Hey everyone, today we will be implementing a fully functional text-to-speech system, or a TTS system. The architecture that we're going to be doing here today is the Tacotron2 architecture. It's a little bit old, but it sets up a lot of really important ideas for modern day TTS systems. So this won't be using transformers. It's a LSTM, a recurrent based system, but that's totally fine. You could almost swap in a transformer, and a lot of the modern architectures that use transformers kind of do a lot of the same things. So we'll just be sticking to a default implementation here, and we will go from there. Before I keep going though, I do want to make two references here. This code is largely based off of two different things. First, of course, the NVIDIA implementation of Tacotron2. So you can go ahead and take a look at that. And then also this awesome reference implementation, which my implementation is a little bit closer to, by Kai Toksu. I'm sorry if I mispronounced your name, but so yeah, go ahead, give these two repositories a star, because they essentially inspired a lot of this code. And so we're going to be doing a quick walkthrough of the architecture right now, and then we'll start implementing it piece by piece. The main idea behind most TTS systems is that they don't typically generate waveforms directly. What they do is generate this intermediate representation of audio or speech, the Mel spectrogram, and then from that spectrogram we can then go ahead and actually generate the audio itself. So there's basically two things going on here. First, if you're uncomfortable or if you don't know what a spectrogram, Mel spectrogram, that stuff is, go ahead and take a look at my intro to audio processing video. I'll link it down below. That's kind of the main prerequisite to this, other than just knowing PyTorch. So go ahead and watch that first, and once you've seen that, you can come back here and this will all make a little bit more sense. But Mel spectrogram is essentially a time frequency plot of what are the different frequencies in an audio at different time steps. And Mel spectrograms especially are essentially a projection, a nonlinear projection of the original spectrogram information that makes it a little bit closer to the perceptualness of speech. Because human speech and human audition, how we hear things, there's a perceptual component to it, and the Mel spectrogram is essentially just a function that applies to the original spectrogram, that just rescales our information such that it falls more in line with human perceived audio rather than just raw frequency information. But I'll just kind of keep it there. So our goal is we want to essentially take text, raw text, characters, and somehow generate a Mel spectrogram from it. And then from the Mel spectrogram, in the original Tacotron implementation, the Mel spectrogram is passed to a WaveNet architecture, which then actually generates the waveforms that we listen back. Today, we're not going to be focusing on this part here. This part here is called a neural vocoder, right? So a vocoder is something that essentially takes a spectrogram and produces waveforms. We won't be doing that today because I'll just make the video way too long. And more modern today is implementing the hi-fi GAN architecture, which we'll get to in the future and is already in my Git repo, so you can see it there. So we're going to ignore that. But then you might be wondering, how do we go from Mel spectrograms to waveforms? Well, we actually already have a really cool signal processing method for that, the Griffin limb algorithm. The Griffin limb algorithm came out way before, and the Griffin limb algorithm's main purpose is it's just a iterative linear projection method to estimate the missing phase information in our spectrogram to essentially be able to regenerate the waveform. We'll just be using a de facto Griffin limb algorithm implementation, so if that didn't make sense to you, it's no problem. But the main thing is the Griffin limb algorithm takes a spectrogram and then converts it to a waveform. Simple as that. We cannot actually get the best audio, so we'll be talking about this. The Griffin limb algorithm, although it technically works, does not really give the best audio representations, and that'll kind of define why neural vocoders are so important. So here's kind of the general idea for our model. What we do is we first start with input characters. So it's essentially just a character level model. I think there's 26 plus a couple of extra letters or characters, tokens, whatever it may be, for our input text. We'll see what that tokenizer looks like in a bit. We embed them just like any other language model out there. we'll embed our characters. It's like a character level language model. But of course, we want the relationship between the characters, so they followed up with 3 different convolution layers and then a bidirectional LSTM. So we learn some local information, right, through the convolutions, and then we learn some sequence information through the LSTM. And then all of this information is basically our encoded text. Now, how do we generate the Mel spectrogram? It's done in a interesting way. So we start with a start token. In our case, our start token is just going to be a vector of zeros, but you can imagine in like language models, whenever we do a GPT type model, there's always a start of sentence, end of sentence. So we start with the start of sentence. We start, some starting point, and we pass it through something known as the prenet. The prenet essentially is just a projection of that starting point. And then what we do is this prenet then goes through 2 different LSTM layers that has this thing called location sensitive attention. Location sensitive attention is different from the standard attention mechanism that we've become accustomed to with transformers. So we'll kind of unpack that as we implement it. And then we produce an output, right? This will produce basically one vector goes in, one vector time step comes out. And then 2 things happen with this vector. One, it goes to a linear projection to predict. Are we done generating? Because we don't explicitly have an EOS token, end of sentence token, like we do in language modeling, but the model needs to know, when should I stop generating my Mel spectrogram? When am I done? When have I generated enough of these Mel spectrograms? Enough of these time steps of my Mel spectrogram. So that's the stop token. I need to predict, when should I stop? And then also it goes through another projection and then goes back to the prenet again. And then basically there's a cycle here. We just loop over and over and over again until we've generated all the time steps, until we've generated a stop token, right? So we just keep doing this loop, prenet, LSTM, linear projection, prenet, LSTM, linear projection, over and over again until we generate a stop token and we're done. As we're doing that, basically these embeddings can be directly projected to a Mel spectrogram. So basically these output embeddings can be projected and they'll predict the different time steps of this Mel spectrogram and we'd be good to go. But as some help, we typically add this additional postnet as well. So the postnet, you can imagine we have a sequence of Mel spectrogram time steps that we've made one time step at a time. There could be some missing information in there though, because there wasn't like some aggregate information over time. It's just been generated one time step at a time. So the postnet basically looks at our generation and then post-processes it. Adds basically some residual information, the missing information that would have come otherwise. So we'll see what that looks like. It's very simple. It's just a bunch of convolutions that we apply to our generation, and then we just add that to our generated data, and that now becomes our predicted Mel spectrogram. So let's just start piecing all of these together, starting with the data set actually. So it's probably best if we implement how the data set stuff comes together, and then we'll go from there. Oh, there we go. All right, so the first thing we need to do is prepare splits. The dataset we will be working with is, just to keep it simple, is the LJSpeech dataset. Let me pull up the web page for that LJSpeech. There you go. Oh, here we go. Very small public domain dataset. It's about 2.6 gigabytes of data, and it's a dataset of 13,100 short clips of a single speaker reading passages from 7 different books, right? And clips vary in length from 1 to 10 seconds. So this is one key thing. The model we'll be building today is for a single speaker, right? So it can only generate the voice of one specific person. We can also build multi-speaker models, but then we have to include something called a speaker embedding, because the model needs to know which speaker am I specifically generating from or generating for. And so this is the data we'll be using. You can go ahead and download it. When you download it, it comes in this format. You'll get basically 3 different files, a wave folder that has all of the audio files in it, and then you'll get this metadata file that has basically the name of the different audio files and then its corresponding transcript, right? So that's it. So we're just going to do a quick random split because it's all put together. So it's best if we separate it apart into a train test split. So we need import OS from sklearn.model selection. We can just import train test split, and I have a feeling, let me actually open up PyTorch for audio, let me see here. I think I might have put the folder in the wrong place. Let's move you out. Move. All right, there we go. All right. And I need to do a quick activate torch. And let's detach you, move you over here. And we need to do a quick pip install scikit learn, because I guess I already have it. Okay, good. That means I need to make sure you are using torch. There we go. All right, good. Sorry, just a package inconsistency. All right, so now that we have that, we also need import pandas SPD, and we need to import Librosa for all of our audio stuff. So we'll be using Librosa. There's also Torch Audio, but Librosa is just easier to use. And I feel like it's a little bit more standard, so that's what we'll be doing. And so what we're gonna do here is def random split. Actually, you know what? I don't even need to type this code because this is not of interest to anyone. So let's just put this in here and I'll walk through it real quick. There's nothing fancy in here. All we're doing is we're loading that metadata.csv that we saw earlier. We then grab the columns that we want, and the columns we want, so their file path, there's a raw transcript and normalized transcript. The normalized transcript is the one we want because it basically has transcriptions with numbers, ordinals, and monetary units expanded into full words. So for example, if we had like 98, 98 is not something our tokenizer is built to handle, so it'd become 90, right? 98, right? PhD. So it basically spells out all the numbers and stuff like that. So that's the specific transcript we're gonna grab. There's like 1 or 2 rows that for some reason have like nan values, so I just removed those. That was giving an issue earlier. We then grab the full path to the different audio files, and then we just verify that all those paths actually exist in our data, just to, you know, sanity check. And then we grab the duration. This is why we're using Librosa. I just want the duration of the different audio files so I can filter out anything that's too long, just in case you have some type of a OOM error. And we're going to sort them from longest to shortest, right? Longest to shortest. And we do this so the padding is minimized. And we'll see why this longest to shortest actually matters in the future. So that's fine. And then we just go ahead and save it. It produces these two files right here. And so it's very simple for us to just go ahead and actually prepare our data. And once we do, it'll produce these 2 files, which I can just copy over. So let's just copy this whole folder, copy, and we can put it in our new one. Paste. There we go. All right. So when you run that, it'll produce a task metadata. So we have this information right here, along with their file paths or file names and the durations and everything. And then we have our train metadata, same thing. We have our durations, transcript, and everything. So yeah, this is just mostly boilerplate code to just prepare our data. Of course, this will change depending on which data set you're working on. So that's why I'm not going to worry too much about this. Let's just keep going to the parts that actually matter. And the first one is our dataset. We need to actually write a dataset class. And so let's see how this comes together. So pandas as PD, import torch.nn.functional as f. We're going to need import, and let's get rid of you, and let's minimize you. Import torch audio. From torch.utils.data, we're going to need our dataset class. We're going to need import Librosa, and we're going to need from Tokenizer, import our Tokenizer. So probably best if we actually write the Tokenizer first. So let's add a new file, actually I already made it, so let's use that, tokenizer.py. So like I mentioned, our Tokenizer will be very, very simple. We're going to do import torch, and we're going to do class Tokenizer, and it'll have an init, and there's going to be a couple things in it. So the first one, this is the Tokenizer for our characters, right? The input characters that go into our model. And so we'll have a self.eos token is going to be a EOS, right? Let's just call it that. Self.pad token is going to be, let's say it's pad. And then we'll have self.unc token, right? Just in case there's something unknown, unc token, just like that. And so our self.cars, I'll just copy this in. So this is just all of the different characters in our transcript. So we have capital A through Z, lowercase a through Z, and then like an exclamation mark, apostrophe, apostrophe. We have our parentheses, comma, whatever, some basic punctuation. And we see here we have a space, right? So we have an empty space right here for our space character. And we're adding on to that essentially the 3 special tokens that we have. And so these are the collection of all the characters we have in our data. So we can then go ahead and do self.car2index, right? Car2id. It's going to be car ID for, or car I for I car in enumerate self.cars, right? Characters. And then self.id to car, if we have to for some reason go back the other way, it will just be the same thing. I car for I car in enumerate self.cars. Just like that. And we can just go ahead and store some information, like our EOS token ID is self.car2id, self.EOS token, we have our self.pad token ID is self.car2id, self.pad token, and then car2 ID. And then lastly, we have our self.unc token ID is self.car2 ID, self.unc token. And our vocab size is very simply just the length of self.cars. And there we go. That's our setup. So we need to write 2 functions: encode self text return tensor equals true by default, right? We want to return pipes for tensors. And then def decode, right? Self token IDs, right? We pass in IDs, and we can do include special tokens equals false, right? Whether or not we actually want to return back any kind of unc, EOS, pad token, that sort of stuff. We don't really care about the decoding because we just need to encode our text, and that's about it, but we'll just throw it in there just in case. So our tokens is going to be self.car2id car, and this is going to, when we index it, it'll be .get if we use .get. .get allows us to search for a car that we want. If it's not there, then we can set a default unc token ID for car in text, right? We're gonna loop through the text, and that's basically it. And if we don't have a specific character for some reason, then we can go ahead and use our unknown token. And we want to always make sure we end everything with a self.eos token ID, right? And we could have written like a template, but this is easier to do it this way, so we'll just do it that way. And if return tensor, right? Well, that's what we normally want to do. Then tokens is just going to be torch.tensor tokens, and dtype is always going to be torch.long because that's what nn.embedding expects. So return tokens. Not too bad. For decoding, very simple. Cars is an empty list, and we're going to do for token ID in token IDs. We'll loop through every single token. Our car is going to be self.id to car.get. Again, we're going to do our token ID, otherwise self.unc token, right? Just whatever. And then we'll have if include special tokens or car not in self.eos token, self.pad token, self.unc token. So if we want to include one of our special tokens, or it's not one of our special tokens, then we can just go and do car.append car, right? Just go ahead and do that, and we can return just everything put together. Join cars. Should be cars right there. There we go. All right, so nothing crazy. We're just going to be looping through our data and then just storing stuff as we go, right? But we don't really care about decoding because there's never really a chance. There's never really a reason for us to decode our text back, as we'll be generating Mel Spectrograms, right? It's not like we're generating text or anything. Okay, so now that we have our tokenizer, we can go back to our data set. So we have our tokenizer, and let's also throw a, my bad. Let's throw an import numpy as np in there as well. Oh, there we go. All right, so let's write a couple of helper functions, and we'll see why they matter as we go. So we're gonna do def load wave, right? We need a function to load a wave file. Very simple. We provided a path to audio, and we give it a sampling rate. Now, Tacotron2 was trained by default on a sampling rate of 22050. So that's what we're going to be using, and the audio we'll be working with, the LJSpeech audio, is already at this sampling rate. So all the audio is already at the sampling rate, so we don't have to worry about it. So we can do audio. Original SR is torch audio dot load path to audio. Now, like I mentioned, we are going to be using Librosa for most things, but Librosa's load is quite a bit slower than Torch Audio's load from my initial testing. So we're just going to go ahead and use Torch Audio's load here just for efficiency's sake. And if SR, so if the sample rate we want does not equal to the original sample rate, right, whatever the sampling rate of the audio is, this won't trigger for the dataset we're working on, but in case it's different, then our audio, we're just going to resample it. Torch audio dot functional dot resample. We're going to resample the audio from the original frequency is the SR, and the new frequency is our SR, right, the sampling rate that we actually want. And this torch audio returns data in the shape of 1 by like the sequence length. We don't need that extra 1 right now, so we're just going to return audio dot squeeze 0. Let's get rid of that extra dimension. So there we go. That's step 1. We have now gone ahead and created something that can load our WAV files. Now, the next step is we need to be able to compute amplitude to decibels and then decibels to amplitude. So if you remember, whenever we compute a Mel spectrogram, and we'll see what this looks like in a bit when we plot some of these spectrograms, but whenever we compute a Mel spectrogram, we typically don't process the spectrogram directly, but rather it's log spectrogram. That's because otherwise the difference in our magnitudes is too large, so we put in the log scale. So it's much easier to see what's going on. We'll see that in a bit. So we just need a way to convert from our kind of raw spectrogram values to a log scale and vice versa. This is relatively simple for us to do. All we need to do is just convert to decibels. So def amp to dB x, and we can set some min decibel is -100. So we set some threshold. And so what we're gonna do is return 20 times torch.log10, and we're going to basically just apply it to x, right? We're going to this is our standard decibel formula, right? Log base 10 of our data times 20, standard decibel formula. Now, what we want to make sure is the output of all of this is no less than -100. So we can set our clip val is going to be 10 to the power min dB divided by 20, right? So, and then if I do torch.clamp x, and we can set the min is equal to the min dB, this actually handles that for us. Why does it handle it for us? Because if we do, and let's kind of just paste the formula right here, just so it's clear, 20 times torch.log 1e to the -5 will always be -100. Right? So we're just making sure we have a 1e to the -5 here. Well, that's basically what all this is doing, right? We're just rescaling it to be this. So the minimum of x is always 1e to -5. So the minimum of the decibel is just -100, and we're good to go, right? Nothing crazy. If we're converting from amplitudes to decibels, then we also need to be able to go from decibel to amplitude. Well, that's just going backwards, right? So def dB to amp x. And all we need to do is return, we did log base 10. So if we do 10 to the power x, well, that will go ahead and scale it, but it shouldn't be times x, it was x times 20. So we need to divide by a 20 here as well to make sure everything lines up correctly. And there we go. So this is us going from amplitude to decibel, making sure the minimum decibel is always no less than -100, and then going from decibel back to amplitude. So that's step 1. We also have a way to normalize. So normalize x. We had our min dB set to -100 by default, so we can put that back. And our max ABS val, let's just say it's 4. And this is one of the things that I took from the non-NVIDIA implementation, right? So this is one thing. So in the NVIDIA implementation, they seem to train directly on the log values, which is scaled between like -100 and 0 or whatever it may be. I actually saw there was quite a bit of instability when training it that way. So what we're going to do is take each of our time steps of our Mel spectrogram, and instead of it being something between with a minimum of -100 and upper of 0 or whatever it is, we're going to rescale everything to be between -4 and 4. Now, why 4? I don't think it matters. We could have picked a 1 here or a 10 here. I don't know. I'm just going 4 because that's what they used in that implementation. I tried different values. It didn't make any difference. So just pick what you want. But we just want to make sure that every single Mel spectrogram time step that we're predicting is basically centered at 0 and kind of, evenly spaced below and above it. So that's the key idea. So for us to normalize something, that's very simple. We can just do x is equal to, this would be x minus our min dB divided by our negative min dB, right? So it's gonna go ahead, take our data. In this case, it's -100, so it's gonna go from, if the minimum of x is -100, then this is going to add basically 100 to it, and it's going to be 0. And then we're going to divide by this, but that basically still stays 0. So there's nothing, that doesn't really matter. And then x is going to be 2 times max ABS_val times x minus max ABS_val. So this is going to go ahead and rescale it, right? We're going to take our max val, set it to, if it's 4, then we have 8, multiplied by x. So this will scale it to basically 0 to 8, and then when we subtract 4, it becomes -4 to 4. But just as a sanity check, we're going to do x's torch.clip in case there was, some extra values that popped out due to imprecision or whatever. We're going to make sure it's between minus max ABS_val and max's max ABS_val, right? Nothing too crazy. So all this does, this function, is it takes some data x that's scaled between -100 and if it was with 0, then it would be good, but typically it'll be something slightly bigger than 0. So it's going to rescale everything roughly between -4 and 4. And then we just clip everything to be actually between -4 and 4. And if we normalize something, then we also need to be able to write the denormalize something, right? So x, again, min dB is -100. And we have our max ABS_val is 4, right? Again, just to keep everything the same. And so we're just going to go the other way. So if we take some data, we need to first make sure it's between, x is between min equals negative max ABS_val, and our max is max ABS_val. So we're going to make sure our data is clipped between -4 and 4, because our neural network will be predicting vectors of magnitude between -4 and 4, right? The values should be between -4 and 4. So we're just going to make sure that that actually does hold true by clipping it here. And then we're going to do x is equal to x plus, we're going to go exactly backwards. So x plus max ABS_val divided by 2 times max ABS_val, 2 times max ABS_val. So we'll go ahead, rescale it. We have everything between -4 and 4. Adding it will make it go from if we add 4, then it's going to be from 0 to 8, and then we're going to divide by 8. Now it's 0 to 1, right? So, and then we're going to do x is equal to x times negative min dB plus min dB, and that's going to go ahead and put it back between -100 as the minimum, and we are good to go. So just, you can go ahead, just follow the math if you want to do it on pencil and paper, but basically these two methods here convert to decimal and then just convert back from decimal, and then this one normalizes our data and this one denormalizes it, and it's as simple as that. So next step, we need the method to take our audio and convert it to Mel spectrograms, right? Because in the end, we're not predicting audio, we're predicting Mel spectrograms. So our training data needs Mel spectrograms. So we're going to do class audio Mel conversion, let's call it there. And this is going to take a couple things. So the first thing is, how many Mel bins do you want? Modern models seem to use like 120, I don't know, maybe like 128 or something like that. But this Tacotron seems to use 80, so we're going to be using 80 here. And then we'll have a sampling rate. Again, this is 20050 by default. We have the number of FFTs that we want. In our case, it's going to be 1024. And also, to keep it simple, our window size will also be 1024. So in our Mel spectrogram, every single bin, every single time step in our Mel spectrogram will have 80 bins, and each one will represent 1024 time steps, right? 1024 time steps in our thing. Now, of course, these window sizes are 1024, but we need some kind of a hop size, right? So we're going to do a hop size hop size is 256. We're going to move over 256 every single time. And so there we go. That's all we have. And then we need to set some fmin. We'll set it to 0. So that's the minimum frequency we want. Fmax. This is kind of up to you. Now, technically, like we talked about in Nyquist, our maximum frequency we can represent is half our sampling rate. So in this case, it'd be 11,025. But that's typically a theoretical max. It never works out always that way. So in the Tacotron implementation, they set the Fmax to be slightly lower. So we're doing 8,000 instead. But you can play with this and see what else. I'm sure you could make it higher than 8,000 and get away with it. So that's fine. We'll have center equals false. We don't really... Center equals false. You'll see what that is in just a second. We had our min dB again as -100, and our max scaled ABS was 4. But again, you could set that to whatever, and it'll probably still work. Self dot, I'll just copy this part in because no one wants to watch me write a bunch of class variables. So I'm just going ahead, store all these things as class variables, nothing fancy. And we need to do two things now. We first need our method to convert our spectrogram, standard spectrogram, to a Mel spectrogram. Well, this is actually pretty easy because Librosa has a, you can basically get the filter bank to do that. So what we're going to do is self.spec to Mel. It's going to be self.get spec to Mel proj. There we go. And we're going to write this def get spec to Mel proj. And it'll be self, nothing goes into it. And I'm going to throw a pass in here, and let's test this out now. Main. Oh. We're going to do audio Mel conversion. There we go. Okay, and I'll call this AMC, audio Mel conversion, right? All right, so this is going to be, let's do a, let's actually keep the pass in there and make sure everything works. Oh. Python, yeah, Python, oh. Dataset.py. Let's make sure everything imports. Okay, good. Yeah, so we're good. So when we run this, what we're going to do is Mel is going to be a librosa.filters.mel. So what this is going to do, we're going to first provide it self.sampling rate, nFFT is self.nFFT. Our nMels is equal to self.nummels. Our fmin is self.fmin, and our fmax is self.fmax. Oh, fmax. So when you print out our Mel, what you'll see, and we'll look at the shape of it in just a second. When you print out our Mel, you're going to get this weird looking matrix, right? This weird looking matrix. And what this matrix does is this. When you look at the shape of it, you'll see it is a 80 by 513 matrix. Now, what do these numbers mean? The 80 is how many Mel bins you want. In this case, 80. The 513 is 2 divided by, or nFFT, 1024 divided by 2 plus 1. Right? So because we set this to 1024 here, it's going to be 1024 divided by 2 plus 1. If we set this to 1,000, if we set it to 1,000, then you'll see it'll be 501, because 1,000 divided by 2 is 500, and then 1. What this matrix is the projection matrix that lets me take a spectrogram with 513 bins in the original frequency space and project it to the 80 bins I want in my Mel space, right? Because this is, again, it's just a projection. It's just a formula that goes from however many bins you want to how many frequency bins you want to however many Mel bins you want. So it's just a matrix multiplication, and we'll see how that applies in just a second. But luckily, Mel, the Librosa, can just give us this matrix without us having to really do much extra effort. Of course, we could write a function that creates this matrix, but we don't really need to bother with that. I do plan on doing a from scratch series for a lot of these different audio processing methods, but for now, let's just stick to simple things because we're focusing more on the model here today. So we now have a way to convert frequency bins from the original spectrogram, a standard short-time Fourier transform, and project it to our Mel spectrogram. And now that we have that, let's go ahead and actually apply it. We're going to do def audio to Mel. Self audio do norm is, let's just say false for now, right? Just so we can see things happening. And so what we're going to do is if not is instance audio. If it's not a torch.tensor for some reason, then we're just going to make sure it's a audio is torch.tensor. We're going to pass in the audio, and we're going to make sure the D type is torch.float32. And our spectrogram is going to be very simply a torch.stft, right? Torch already has a short-time Fourier transform that we can use, and I can go ahead and just actually copy that in, right? Nothing crazy. So what we're going to be using is we're going to apply a short-time Fourier transform on our audio, and we have this NFFT size, how many frequencies want, the size of our Fourier transform. We have our hop size, we have our window size, we have the window that we want to use. Now in this STFT, in the original implementation, they seem to just use the Han window, and that's going to be totally fine. But you could use Hamming window or anything else. I'm not sure if there's a theoretical benefit to different window types. I'm assuming regardless of what window you use, as long as it's reasonable, then the neural network will just kind of end up learning it anyway, so it's probably fine. Again, if you don't know what a window is, go ahead and take a look at that initial audio processing video, right? So you can kind of learn about what different windows are, but we're just going to go with the default here, right? Just standard window. And we need to make sure if we're using the Han window, we have to make sure it's on the correct device, right? We don't need to center it because it doesn't really apply for us, so we don't, that's why you center as false up here. We can then go ahead and do reflect padding, just in case, of course our window will spill over, so we need to make sure we reflect it to make sure we don't add on extra stuff. We could, if we did zero padding, then we would essentially have audio and then an immediate stack of zeros at the end, and that'll add some artifacting because there's such a quick shift from information to no information. By doing reflect padding, then that doesn't happen anymore. No need to normalize because we will be doing that ourselves. One-sided is true because we're just doing it on one side, and we're going to return complex, and you'll see what that looks like in just a second. So if we print our spectrogram out, let's go ahead and actually apply this to something. So we need to grab an audio file. So let's see, what's the best way to do this? Let's just grab one of these paths to the audios. So let's go here, let's go here, and I'm just going to grab one of these paths to one of my audios, and we can test it out. So we will have here path to audio is that. So that's the audio file we'll be working with. And then we will have our, let's see, we need to do our load wave file. So this will load our audio file all ready to go. So we can actually test stuff as we're going. Load wave, path to audio. Everything will be the same. If we print out our audio, it should just be a simple vector of values. There we go. Looks like we got a warning because some parameters like normalize format will be ignored. Okay, that's fine. Just ignore that. We don't really care about that right now, and we can actually, I think this will work. Import warnings, warnings.filter warnings. How do you do this again? Let me check filter warnings. There was a specific way. Oh, it was just ignore. Okay, yeah. So there you go. Let's just ignore warnings for now because we are not really dealing with that. There you go. So we now have our vector of audio values, right? That's our audio file, our waveform right there. Okay. So now that we have that, what we want to do is apply audio to Mel on this specific audio. So let's go ahead and do that. So let's do audio. We're going to do amc.audio to Mel on our audio. And now if we print our spectrogram out, we should see something like this. So we have our spectrogram here, but notice that every value is a value plus a complex value because this is a Fourier transform, right? So we have both magnitude and our magnitude and phase is represented by these complex numbers. And so we don't really need the complex values. we just want the magnitude. So to get the magnitude in Torch is very simple. We can just use ABS, right? Torch.abs will essentially extract that, extract the magnitude for us. It's just the, it's basically just the Pythagoras theorem, right? On our real component, a square of the real component plus the square of the complex component squared over that. So nothing fancy. So our spectrogram is going to be torch.abs spectrogram. So now we have actual data, right? So that is our spectrogram. If we look at the shape of the spectrogram, you'll notice it is 513 by 656, or 657. So we have 513 frequency bins by 657 time steps that this thing produced. And that's why this thing, our Mel bins here, also had 513. It was exactly for that same reason. Now that we have that, let's go ahead and convert it. So we're going to do our Mel is going to be torch.matmul, and we're going to do self.spec2mel.2 spectrogram.device. We're going to make sure that the thing we're multiplying by, the spec to mel thing here, we're going to make sure it's on the correct device if we're doing it on GPU for some reason, and then spectrogram. And there we go. So this is essentially going to go ahead and multiply our two things together, matrix multiply, and we finally get our Mel bins, just like that. Now, here's the problem with the Mel bins directly. So what we're going to do is throw another import matplotlib.pyplot as plt. So you've probably we've probably seen this before, but just for any new viewers, let's just make sure we're being thorough. plt.imshow mel plt.show. What you will notice is this. Notice, like, oh, let's pull that back. So we have here basically our data of number of time steps. So there's 657 time steps. And we have our 80 different Mel bins that we asked for, right? And that's what our spectrogram projected to. But notice, like, most of the image is kind of like empty. Like there's nothing in here in this plot. I mean, we can see the peaks, right? The highest frequency stuff, and these high frequencies are basically those the information we really care about, right? This is what determines that pronunciation of the different utterances as we're saying the thing. But the other information does matter, right? The harmonics and all of that. And that information's kind of lost here, and the neural network will probably struggle a little bit. And we can check this if we do print mel.min mel.max, you'll see something like this. We can see our min is, very small, like basically 0. Our max is 1.5537. All of that is fine. It'll probably be best if we rescale it, right? And this is why we wrote that method to scale. So let's first do mel is going to be amp to decibel mel, right? So we're essentially just doing the log transform of this scaled by 20, but that's honestly optional. It doesn't really matter whether or not we do it. It just makes sense to do it that way. And when we do transform to mel, we need to do with the self.min decibel, right? Make sure the minimum is there. And now we will see way more information. So when we put it in the log space, you can actually see a little bit more information of what's going on, right? Those harmonics, the bands, all of that sort of stuff. So we can, this is better, right? This is much, much, much better. Okay, good. So we have our spectrogram, right? We have our Mel spectrogram. Now, of course, like I mentioned, we want to, and let's actually print mel.min, mel.max. When we convert to Mel spectrograms, we can see that the min is about -100 and the max is about 4. And neural networks will probably struggle to train on data like this, right? Because it's so lopsided. We'd rather have nice normalized data that we predict, and then we can always denormalize it after the fact, which is why we exactly wrote that method to deal with our spectrogram. So if we do if do norm, which we want to during training, and always really, we're going to go ahead and normalize with our normalize function. Mel, we're going to pass in the min db is going to be equal to self.min db. Our max ABS spell is again self.max scale ABS, and that should be good. And so now if we print our mel.min, mel.max, we should see that it should be between, oh, I need to set do norm to true. So we're going to do audio to mel, and we're going to do norm to true. There we go. Now we can see it's between -4 and 4. So we just rescaled our data between there. When we inference, we need to unscale it, but it will be good to go, right? So there we are. That is our data. So we can now return mel. And that is essentially it in terms of taking our audio and creating the Mel spectrograms that we're going to be training on. Now, of course, we also need to go from Mel spectrograms back to audio. And this is where we'll be using the Griffin lim algorithm. Now, one thing to keep in mind is the Griffin lim algorithm only applies to spectrograms, not Mel spectrograms. So the first step is we need to take the Mel spectrogram we predicted and go back to normal spectrograms. And then we can take the normal spectrogram and apply the Griffin lim algorithm, and we'll be good to go. This is a little bit more challenging than I just said, but that's okay. We'll get through it really quickly. So mel to audio, it's going to take a it's going to take a mel. It will take do dnorm equals false, and then Griffin lim iters, right? Lim, because this is this is basically a bunch of iterations of a bunch of linear projections, and then we're just going to set that to like 50 or something, right? It should be enough. We can change that later. It's just a bunch of projections, and we'll be using a default Griffin lim algorithm to do this. So the first step is we need to do if do dnorm, we need to do mel is equal to denormalize mel min db is equal to self dot min db, and max abs val is equal to self dot max scaled abs. So this is going to go ahead and take our -4 to 4 and just renormalize it to be between with a min of -100 and all that. So it's just undoing the step. The next thing we need to undo is this one right here. We're just going backwards in the process. So we first the last thing we did was normalize. So the first thing we do is denormalize. The second to last thing we did is convert to decibel. So the next thing we do is convert back to amplitude. So that's easy enough. We can do our mel is dB to amplitude. Oh, right, that's why we wrote that method. And then what we're going to do is recover our spectrogram. And this is the hard part. How do I go back from here? If I had a thing here that I multiplied, I took my spectrogram and multiplied it by this thing. How do I undo its multiplication? Well, that's easy enough. If you multiply by something, if you had y is a x, if we want x back, right? If we want x back, that means x is just equal to y over a. So we just have to divide by the thing. Now, this is a matrix multiplication, right? This is a matrix multiplication, which means we don't divide by something. If we do y equals, let's say, our mel times x, that means x is equal to our m inverse, right? Inverse. Let's do it this way. Inverse. Y, right? So if we just take the inverse of this matrix and multiply by that'll undo it, right? So that's no problem. That kind of works. Except there is one small issue in the sense that our Mel thing here, this Mel projection matrix, is not a square matrix. You can only take the inverse, the true inverse of square matrices. And so if it's not square, we can't take the inverse. Luckily, we do have an approximation, and this is our pseudo-inverse, right? The pseudo-inverse is essentially just, it's what linear regression typically uses. So it'll be self dot, we're going to create a mel to spec, right? So it's going to go backwards. And what we're going to do is torch dot linalg dot p in. So this is a pseudo-inverse, self dot spec to mel. So you can look this up. What pseudo-inverses are, but it's essentially just an approximation of what an inverse could be, though it's not a perfect inversion, right? Some information is lost. But either way, that's fine, because we'll be doing neural vocoders in the future, and we won't care about this line here anymore. But this is just for now. This should work. So this is a pseudo-inverse to take our, if this is the matrix that goes from spec to mel, and this is the true matrix that takes our spectrogram, projects it to Mel spectrogram, this is an approximation of going from Mel spectrogram back to the original spectrogram. And that's our pseudo-inverse, right? P inv. All right, so now that we have our spectrogram, to get our spectrogram, all we need to do is torch.matmul between self dot the pseudo inverse, right? Mel to spec dot to mel dot device. Make sure it's on the right GPU, and the mel. And then we're going to make sure it's on the CPU and then numpy, right? Because that's what we're going to do it here. And then audio is going to be librosa.griffinlim. S is our spectrogram. This is the thing we're going to be applying Griffinlim to. And iter is going to be our Griffinlim iter. And then we should provide some information of the spectrogram, like the hop length was self.hop size. Our win length is self.window size. Our nFFT is self.nFFT. And then our window, the window we used, was the Han window, right? So we're going to keep that the same. And this will go ahead and produce our audio. Nothing too crazy. Now this will produce audio between 0 and 1, or I guess minus 1 and 1, whatever it may be, I can't remember. But we typically save audio in like int16 format and all that. So we're going to just do standard scaling. So audio is going to be audio times equals 32767, right? That's the max we want, divided by max 0.01 np.max np.abs audio. So we're going to make sure that the maximum value that our audio can represent is this, because this is essentially between -1 and 1. This is the highest that floating point, like int16, can represent. So we're going to go ahead and convert to int16 and return our audio. So that's it. So this is essentially our audio processing to convert to Mel Spectrograms. Now that we have all of that, we can go ahead and start our actual dataset class. So we're going to do class TTS Dataset. This could be a standard PyTorch dataset, nothing crazy. And I'm going to go ahead and just copy the beginning of all of this, just so it's easy. We already know what all this is. The only thing I've added in is my paths to the metadata, right? The CSV file that we want to load from. And so now we're going to have, let's do self.transcript lengths is going to be len tokenizer.encode tokenizer.encode t for t in self.metadata, right? Metadata, and we're going to do our normalized transcript. So what we're doing here is we're just looping through every single sample in my data, and let's throw another parenthesis right there. Don't need you right there. Looping through all of my data, looping through all of the rows of my normalized transcript, and just grabbing the length of those transcripts, just so we can save that for the future. So that's fine. So we just have that for later. And then what we have is self.audioproc, right? Audioproc is going to be our audio Mel conversion, right? This is the entire thing we just wrote earlier, and I can actually copy this in as well, just so I don't have to type all of this out. This is everything we just wrote, right? Audio Mel conversion, conversion. Okay, this should have a S right here. So let's put that in there. S right there. So yeah, that's basically everything we wrote, right? The thing that takes our data, converts it to Mel Spectrograms. Our len, very simple. This is just going to, we can return len self.metadata, which is just a pandas, right? CSV file, nothing crazy. Good, so there's our data, there's our len, and now our get item. Def get item self index. And what we're gonna do is our sample is self.metadata, and it's a pandas data frame, so we can do .iloc index, so that'll grab a specific row of our CSV. Our path to audio is going to be sample file path, and our transcript is going to be sample normalized transcript. And then our audio is going to be the load wave file, or function that we wrote, path to audio, and then it's going to be our SR, self.sample rate. And then we take this audio, convert it to a Mel spectrogram. So we're going to do Mel is equal to self.audioproc.audio to Mel, audio, do norm equals true, right? We always want to normalize when we're training. And we're going to return our transcript and mel dot, we don't need that extra dimension. It'll return a 1 by, height by width, or time steps by, or mel bins by time step. We don't need that, so we're going to go ahead and squeeze that dimension. And there we go, very simple. Just a TTS dataset that returns our transcript and our mel bins. Now, of course, we don't directly train on this. We need to write a collate function because every single audio file has different length audios, different length transcripts, right? So a little bit more work to do. So we're going to do def TTS collator, and our tokenizer is going to be the tokenizer. Now I think about it, I don't think we actually need this. So I'm going to just comment it out for now. I don't think we actually need it for anything. Def collate function batch. So let's go ahead and write our collating function. So our text is going to be tokenizer dot encode B0 for B in batch, right? We're going to loop through every single sample in the batch. Each sample is a tuple of these two things. And the first thing, or the 0th thing, is our transcript. And the second thing is the Mel Spectrogram. So we're going to go ahead and grab those. And then our mels is going to be B1 for B in batch. Go ahead and grab those Mel Spectrograms as well. Now what we need is the length of all the texts and the mels. So we're going to do input lengths, GPH, lengths, is going to be torch.tensor, and we're going to do t.shape 0 for t in text, right? This is the length of every single transcript, right? How many tokens are in every single transcript. And dtype is going to be torch.long. Similarly, our output lengths, these will be our spectrograms, is going to be torch.tensor, and it's going to be m.shape, shape 1, right, for m in mels. The reason it's 1 is because each Mel spectrogram is 80 by number of time steps. So it's the second dimension that is our thing, right, is our length. And this again will be dtype is torch.long. So this is the length of our input and the output. Now there's one key thing we need to do here is we need to sort our data by length. The reason we need to sort it is because we'll be using packed padding. So in PyTorch RNN, we have something called packed padding, which we've seen earlier, though I can't remember which video it was anymore. But in one of our previous videos, I'll find it and I'll link it. We use packed padding, which essentially allows us to train RNNs on sequence data that's padded without actually computing on pads. Because pad tokens, the extra pad we add to make sure all the sequence lengths are the same, are unnecessary. It's wasted compute, and RNNs are expensive already, so why would we want to loop through more pad tokens and make compute even more expensive? So we want to use packed padding, which we'll see how it works out in a bit. The only downside, or not downside, but the only limitation for packed padding is we need to make sure that our data is sorted from longest to shortest. So in every single batch, the first sample has to be the longest thing. The second sample is the second longest thing. The third sample is the third longest thing, ... So we're just going to do that. This will be applied specifically on our text encoder. So we want to make sure that the input lengths, these input lengths here, are sorted from longest to shortest. So we're going to do input lengths sorted index is going to be equal to input lengths dot sort descending equals true. This is going to return two things. The sort index, right? So if we had the lengths, let's say 5, 2, 8, 7, then LENG lengths. So after we sort it, this is going to become 8, 7, 5, 2. 8, 7, 5, 2, sorry, right? That's sorting it from longest to shortest, 8, 7, 5, 2. And the sort index tells me that the 8 is the 0, 1, 2. So it's the second sample. The 7 is the third sample. The 5 is the 0th sample, and the 2 is the first sample. So the sorted index tells me that. So the input length gets sorted, and the sorted index tells me the sort order, right? The index is from the original position. The reason we need the sorted index is if we sort our input lengths, we need to also sort our output data, right, in the same order. So let's go ahead and do that. So our text is going to be equal to text I for I in sorted index, right? Go ahead and take our text data and sort them according to the sort index, which provides these input lengths. Our mels is going to be equal to mels I for I in sorted index, right? Go ahead and sort our mels in the order of the longest text to the shortest text. So the mels may not be the longest mel to the shortest mel. Obviously, there's a correlation, right? The more characters you have in your text, probably the longer your mel is, but it's not perfect. So, but that's okay. We're not doing packed padding on the mels. We'll see how we handle that later. And then our output lengths is going to be output lengths, and we can just do sorted index here, right? Go ahead and just resort this in the order of whatever was longest to shortest in our original text. Good. So now we can do our text padded is torch.nn.utils.rnn.pad sequence, right? Go ahead and do that. We're going to do text. We're going to do batch first is true. And our padding value will be our pad token, right? So the padding value is tokenizer token ID. Very simple. And then we have we need to also pad our mel sequences. So our mel target len is going to be equal to, what's the longest mel we have, right? That's going to be max output lengths dot item. This gives me the longest mel sequence that I have. And our num mels is going to be mel 0 dot shape 0. This should be 80, right? We have 80 mels in this thing. So that means what we can do is create a setup like this. What we're going to do is create an empty tensor. We're going to do mel padded is going to be equal to torch dot, everything's just zeros right now, right? Zeros. And it's going to be len mels, and we'll have num mels by max target len. Am I missing max target len? There we go. This should be max target len. There you go. So I've created a zero tensor that has batch size, number of things we have, by num mels 80, by whichever sample in this specific batch is the longest, right? And we basically have this big block of zeros, and now we're just going to fill in the corresponding parts, and everything after that length is just, zero. So very simple. And another thing we need is gate padded. This is again going to be torch.zeros, len mels, max target len. And we'll see what that is in just a second. What we're going to do is for I mel in enumerate mels, loop through every single mel. T is equal to mel.shape 1. This is how many time steps are in this specific mel that we're looking at, because we're looping through them one at a time. And then mel padded, we're going to do for this specific batch, for all mel bins, all 80 of them, up to the tth position is equal to mel. And then we have our gate padded is equal, for this specific batch, for every t from this one and forward, so t minus 1 to the n, is equal to 1. And then our mel padded is equal to mel padded dot transpose 1, 2, because typically our data right now is batch by 80 by sequence length, but typically we work on batch by sequence length by like an embed dim, right? So we want to make sure that the sequence length is first, and then we can return our text padded input lengths mel padded gate padded, and one more thing that we're going to write in just a second. Now, this gate padded is this. If you remember, we need to predict the stop token, which is going to be, in our case, it's going to be 0 when we don't want to stop, and 1 when we do want to stop. And we have in our data when we should stop. So we're just creating that here. Basically, we have, imagine if our Mel spectrogram was four time steps, then we'd have 0, 0, 0, and then 1. We want to stop at this last time step, which is why it's t minus 1 here. Now, of course, different samples in the batch are longer than other ones, which means that if this one here is, let's say we had another one that was longer, so it was 0, 0, 0, 0, 0, 0, 0, 1. Right, so let's say this is longer, we want it to end right here. That means we're just going to pad all of these, because this is all n token, right? So we're going to just go ahead and pad everything with 1s, essentially. And that's what you see happening here. So you just create a canvas of zeros and fill in with 1s everything from t-1 to the n, because these are all essentially stop tokens, stop generating. For the Mels, we create a canvas of zeros, we loop through every single sample, and we just fill in up to the tth time step that Mel spectrogram. And there we go. That's what we have here. We need one more thing, though, of course. Anything extra that's in padding, we don't really want to compute loss on, so we just need a padding mask to do that for us, right? So let's just create a quick method here that will build a padding mask for us. So we can do def build padding mask. It's going to take some lengths parameter, and we're going to do b is equal to how many samples do we have? Batch size. It's going to be lengths lengths dot shape 0. Wow, I always spell lengths wrong. Lengths dot shape 0. And then we have our t is going to be torch.max lengths.item, right? Item. And so this tells me how many samples do I have, what's the longest thing, just like we did before. And then we'll do a mask is torch.zeros_bt, and we'll do for I in range b mask at this specific sample for lengths for this specific I to the end is equal to 1. Return mask dot. Cool. So this basically tells me which time steps are padding time steps and which time steps are not padding time steps. And this lets me make sure when we actually compute our loss, we don't include any kind of pad tokens in our loss function, right? So there we go. And so we just need to use this method very quickly, and this will give us essentially this, right? We have our, we'll do it twice. First for the input lengths, right? So these are the padding masks for my inputs. And then we'll also have the build padding masks for the outputs. And that is everything that we need to return. Okay, I think that should be good. Let me double check real quick to see if I'm missing anything when we go to train this. Okay, yeah, let's do one more thing. Okay, let's do this. So we need to also write a batch sampler. And this more has to do with efficiency than anything else. The thing is that when we grab random batches, of course, like every single random batch will have essentially, different amounts of time. But it's kind of a waste of compute to have a bunch of samples that are very different in the amount of time, because then we just end up computing stuff that we don't really care about. So what we want to do is essentially create a batch sampler that just groups things together that have similar amounts of time, number of time steps, and just do it that way. So we're basically doing random sampling between groups of stuff that have similar amounts of time. And that way training is a little bit more efficient. So let's go ahead and do that real quick. Init self, we'll have the data set, we'll have our batch size that we want, and drop last is false, right? And we'll see what that is. So self.sampler is, we can just use an existing one, torch.utils.data.sequential sampler. This is the default that PyTorch uses, right? Just sample in order, data set. And then self.batch size is our batch size. Self.drop last is drop last if we want to get rid of that last sample, because the last chunk of samples will of course have potentially a different number of samples in it, because the number of samples in our data set may not be perfectly divisible by the batch size, but this doesn't really matter for our case. Self.random batches is equal to self.make batches. So we need to write a quick method that creates these kind of buckets essentially of batches that we sample from. So make batches. And how this is going to work is indices is going to be very simply I for I in self.sampler. Basically we have 0 to number of samples that we have. And if self.drop last, if we wanted to drop the last one, then our total size is going to be the len of our indices, right? So how many samples we have, divided by self.batch size times self.batch size. So go ahead and do integer division of how many samples we have. By this, it'll round down, and then we just multiply by batch size again, which just gives us, the final amount. And this would obviously be missing stuff. So for example, if we had 5 indices and a batch size of 2, then 5 integer division by 2 is 2, and then times 2 is 4. So this would only include the first 4 samples and just ignore the last one, but that's fine. And then our indices is just going to be the indices, and we're going to just filter out for only the first total size amount if we want to remove that last batch. And our batches is going to be indices I to I plus self dot batch size for I in range 0 to len indices. Am I missing one? Yeah, 0 to len indices. And when we do range, we want to do them in chunks of self dot batch size, right? So in chunks of self dot batch size, and then our random indices is going to be torch dot rand perm, a random permutation of len batches, right? So we're going to do a random sort of these different sequence lengths, and then we can return batches I. Let's put this right here. Batches I for I in random indices, just like that. And so then def iter, right? How do we actually iterate? Iter self. All we do is for batch in self dot random batches, we can yield, right? Yield, basically return, but yield our batch. So this way we can pass it to a generator object. And then def len is self return len self dot random batches. So this is essentially just our how many batches do we have in our data set. You might notice here though, where is our sorting? Like I mentioned, right? We wanted to make sure that our different samples, like different samples when you grab them in batches, kind of have different or have similar lengths, right? Similar lengths, but we don't really see that here. The reason is because the sequential sampler already goes in order from, you know, smallest to largest, smallest, however it may go, right? Whatever order your data set is going in. But in our case, we already did the work in prep splits to sort everything from longest to shortest, which means as we go through things sequentially and we grab batches, sequential batches, right, consecutive samples already have similar lengths because I've already sorted it ahead of time in my data preparation. If I didn't pre-sort it in the CSV, then I would have to do that work right here to grab the length of everything and then sort it here and then produce the batches. That's more work, right? Who wants to do that? So it's easier just to pre-sort it and then make sure we chunk our batches into these chunks and then do a random permutation of those chunks where each chunk has similar lengths, and we are good to go. So that's it. Very simple batch sampler. Good. So that is all we needed, I believe, for our data loader, right? So that was the less interesting part. Now we can go ahead and, let's see, we did our tokenizer, we did our preparing of the splits, we did our data set. So I guess all we have left now is the model and training. Good. So let's go ahead and start on the model. To do the model, I'm going to go ahead and copy the config file in just so it's easy. So this Tacotron, like I mentioned, has 80 mels, right? So it's going to, every input mel feature, right, has 80 mel bins in it. And then we have our character embed dim. Every single character, our embedding matrix will represent them with vectors of length 512. I have 67 letters in my tokenizer. So I already pre-computed that. So there's 67 things in here, including space. We have our pad token ID, which is 0, as I already checked in my tokenizer. So there we go. We then have our encoder config. We have a decoder config and an attention config. And none of this will really make sense until we start building it. So let's just go ahead and start building it, and then I'll refer back to this as we go. So first we need to define some layers. And what we need to do is our linear norm. This is probably optional, mostly because weight initialization matters, but the NVIDIA repo takes it very seriously of how we initialize these linear and convolution layers. So if they're taking it seriously, we should just take it seriously too, so it's fine. In features, out features, we have bias equals true. So this is our standard linear layer, right? This is what most linear layers do. But we have this new thing here, w init gain equals linear. And we'll see what that is in just a second. Super linear norm self dot init, and we have self dot linear is going to be nn dot linear standard, right, in features to out features, and then we have bias equals bias, so nothing crazy. What changes is the weight initialization. So we're going to do torch dot nn dot init dot Xavier uniform. That's the initialization I decide to use. We'll be initializing the linear.weight, and we'll be using gain is equal to torch.nn.init.calculate gain w init gain. So let me show you what that is really quickly. So Xavier gain, there's a great thing here. So basically the Xavier initial, and a couple of different initialization functions, but in this case, they have different types of initialization, like constants for the initialization, based on the type of activation that's going to follow it. And these are supposed to be ideal. And there's, I don't know, I could, it's fine. I'm not going to go into too much mathematical detail here. But the thing is that when we initialize something, if we know that the activation function that comes after this linear layer is like a ReLU, then this is the best gain to use. If we know the activation function for after our linear layer is a tanh, then this is the best gain to use. And someone basically just did the math, just, you can show this, it's like a variance property or something like that. But regardless, we want to essentially make sure that we're using the best gain depending on the activation function that we know is going to follow. And that's all it is. So we're using essentially this function here, right? This function right here, to init gain. Okay, good. So nothing crazy. You could probably, I don't know, I didn't test without it, but I'm sure if I tested without it, it would work just fine. So yeah, either way, weight initialization, fun stuff. The def forward self x return self dot linear x. So all we're doing is we're going to provide something here based on the activation function we're using, and then based on that, we can go ahead and actually set everything up. Okay, so if we do that for the linear, then of course if we have a bunch of convolutions as well, we can just go ahead and do it there as well. So we have our linear layer, right? So that's the linear that we just did. And then we have our convolution. Same convolution, nothing fancy. Just again, we're going to be doing an initialization based on the activation function that we'll be using afterwards. Okay, so yeah, just keep those in mind, but let's just keep going. We now have our encoder. So let's kind of refer to this picture as we go. The encoder is going to be these 4 blocks right here. We have input text, which goes to embeddings, goes through 3 convolution layers, and a bidirectional LSTM. Each of these character embeddings have a embed dim of 512. My convolutions have a kernel size of 5. We're going to have 3 of them. And my embed dim here is 512 because both of these things match. And then our dropout is 0.5. So these parameters were just taken from the original implementation, right? Just referring to that. But I'm sure you could mess with it and make it even more optimal. Class, encoder, nn.module, def init, self, and config, right? We'll be passing in these config files, and so we can do our super encoder self.init, and we'll have self.config equals config, so you can access it everywhere. Self.embeddings is equal to nn.embedding, and it's going to be config.numcars by config.character embed dim, right? So that's very simple, right? It's just how many characters we have, 67. We are representing each character by a length of 512, so there we go. And then we also have the padding index. This is just the extra index we have. We don't really need to compute gradients for it, so we can do config.paddToken ID. That's what we pass that in. Now that we have that, after our embeddings, we had those 3 convolutions. So let's just create a self.convolutions. It's going to be nn.module list. And I'm going to do for I in range, config.encoder nconvolutions, right? Just loop through each one of them. We'll do self.convolutions.append, and we'll append on the sequential blocks. So sequential. And each of these sequential blocks is going to have a conv norm, right? And I can go ahead and actually copy this block just so I don't have to type it out. Just make it simple. Here we go. We have a sequential layer, we have a convolution, a batch norm, a ReLU, and a dropout. Pretty standard set of convolutions. And the key thing is this, 2 key ideas. 1, our gain is ReLU because the activation function that comes afterward is ReLU. So that's basically why we did this. This is now the quote-unquote optimal initialization of this convolution specifically for a ReLU function. Sure. The other thing is padding is same. We want to make sure that as we do these convolutions, the sequence length size never changes. It should always stay the same length, right? So we're going to make sure that that always stays the case. And so we're making sure that as we convolve over our character embeddings, we're not downsampling or anything. Everything stays the same size every single time. And then we're doing these for the kernel size that we picked. And in this case, it was 5, right? In the very first layer, it'll take the encoder embed dim. So if it was 512, after that, it'll take the character embed dim. So if for some reason this value here and this value here were different, then we have to handle that. Right? The very first one will take 512 from here, but every convolution after that will output, whatever the output was. So it'd be 512 right here. But because everything's the same, we don't really care about that right now. That's pretty simple. So pretty standard. Convolution, batch norm, reloop, dropout. Nothing crazy. That goes ahead and produces those convolutions. And then after those convolutions, we have a bidirectional LSTM. So let's just stick that in there too. We're going to do self.lstm is nn.lstm. This LSTM is going to take input size is equal to config.encoder embed dim. Hidden size is config.encoder embed dim divided by 2. This is how they do it. They want half the size coming out the other end, so that's fine. Num layers is equal to 1. And batch first is true, of course, and bidirectional is true. So it's just a single layer of an LSTM that takes 512 input, produces a 256 embed dim output. It's just one of these, and we want batch first is true, and it's a bidirectional model, right? Because these are characters. It's fine for character embeddings to be bidirectional because we provide the character embeddings up front, right? So we can look both directions. On the other hand, when we're generating the Mel spectrogram, we can't really do that there because, well, we can only look at the past Mel spectrograms to produce the future one. So that's it. So now we can do our forward self x, and of course our input lengths, right? Input lengths. And you'll see why we need that. By default, I'm going to set this to none, actually. If it's none, so we're going to do x is self.embeddings x, right? That's going to go ahead and embed every single thing. But this is now going to be batch by time steps by embedding dim. We just need to make it opposite. So we're going to do dot transpose 1, 2. So this is going to be batch by embedding dim by time step. The reason we're flipping it here is convolutions expect it to be in that shape, right? So the sequence length dimension should be the last dimension. So we're going to flip it right here, and then we'll flip it back again in a bit. We're going to do if input length is not none, is none. If we don't pass an input length, then we're going to assume that the input length is same for everything. So we're going to do torch.full batch size, and we're going to do fill value is sequence len. And the reason this will work out is this. We can do batch size by channels by sequence len is x.shape, right? That's the shape of this tensor coming in. And of course, the longest thing will be of length sequence len, like whatever it is. So we're just going to create a tensor full of sequence len, and that's it. Device equals device. And it should be x.device. There we go. So yeah, that's it. So we're just creating a sequence of just a tensor of just sequence len, assuming this just assumes every single thing is of the same length, and that's it. And now let's loop through our convolution for block in self.blocks. Loop through everything. X is equal to block x. This is me passing my character embeddings through every convolution. And then x, again, is x.transpose 1, 2. Flip it back because now the RNN, or the LSTM, expects it in the batch by sequence length by embedding dim shape. So it's just opposite. Now, here's the key thing. We need to make sure we do the packed pad sequences. So x is equal to pack padded sequence. We imported this above from RNN. Pack padded sequences. And it's going to take x. It takes input lengths. For some reason, these have to be on the CPU. So there we go. And then batch first is true. So this just takes our data, packs it all together, and keeps track of which tokens go with which time steps. So in our case, let's say we had data, let's say it's 1, 1, 1, 1, 1, like there we go. So that's the longest thing. The next thing, let's say, is 2, 2, 2, and then we added some pad tokens here. And then the next thing is 3, 3, and then we added some pad tokens here, right? That's how we would process it. In the case of an LSTM, if we don't do this, we'd have to process everything, including the pad tokens, which would it would still give you the same result. It's just inefficient, especially if you have wildly different sequence lengths. Of course, we handle that by making sure batches are of similar sequence length, but efficiency is efficiency, right? So we're going to make sure we deal with this. So all we do is we take the sequence and go 1, 1, 1, 1, 1, and then 2, 2, 2, and then 3, 3. So we take everything and just pack it into one long sequence. But the input length tells us that if the first thing's input length would be 5, because the first 5 things are actual data. The second thing in this input length vector would be 3, because these 3 things are actual data. And then the next one would be 2, because these 2 things are actual data, so on and so forth. Right? So that's all packed-padded sequence does. And RNNs and LSTMs, PyTorch's RNNs and LSTMs automatically can handle packed-padded sequences. So makes our life very simple. And so outputs, it'll also return some hidden in cell state, which we don't really care about, is equal to LSTM x. And we can now do outputs and blank, because we don't care about the indexing either. We need to just return this back. So if we packed a padded sequence, we now need to repad our packed sequence. So it's just taking that vector and putting it back kind of how we found it. So nn.utils and actually we can just use the pad packed sequence outputs batch first is true. So very simple. It just takes this, which will return it as a packed padded sequence object rather than just a normal tensor like we do in PyTorch. And we can undo that extra like indexing and stuff, because now we're done. We don't really need that anymore. And we can return outputs. And that's it, right? That is our encoder. So that handles these 3 blue blocks. Well, tongue twister. Blue blocks right here. Next, we need to start building all of this stuff up here. So what we're going to start with is this prenet layer, because the prenet layer is basically the start of our model. It takes so the first thing we do is we generate this character embeddings. That kind of stays as a constant. Now, given the condition of these character embeddings, we want to generate the Mel spectrogram. So what we're going to do is the prenet essentially starts with some starting point and then produces an embedding, goes to this LSTM that does something called local sensitive attention, and then it kind of does this loop over and over and over again. So let's go ahead and define this prenet layer. Prenet layer is very, very simple. It's just it's basically just a linear layer, right? Just a linear layer. So let's do class prenet nn.module def init self, and it's going to take an input dim, a prenet dim. We have a prenet depth. How many linear layers do we want? And then drop out p equals, let's just set it to 0.5 by default, because that's what it uses. Super prenet self dot init. Good. So self dot dropout p is equal to dropout p. This is really important. We'll see why in a bit. And dims is going to be equal to the input dim plus prenet dim for blank in range prenet depth. Right, so we're going to start at this input dim and then project to the prenet dim, and then we'll just do that over and over again until we've done however many we want in our prenet depth. In our case, our prenet depth is 2, so it's 2 linear layers. So it's going to go from whatever the input dim is to the prenet dim. So the prenet dim is, let's see here, 256. We're going to go from 2 to, basically we'll go to whatever the input length is, we'll see what that is in a bit, to 256. And then the second layer will just go from 256 to 256. So very simple. And so those are our dims. Let's define our layer. Self.layers is equal to nn.module list. Module list. And we'll do for in dim, out dim, in zip, right? And we just want dims, everything but the last thing, dims, everything but the first thing. I just loop through them. And so the first one will be basically this dims is if we have input 256, 256, it's going to be, this one's going to be these 2 values here, input 256. This one's going to be the second 2 values, 256, 256. So the first in out will be input, and then the out will be 256. The second in out will be 256 input, 256 output, right? Very simple. So now that we have that, let's go ahead and do it. Self.layers.append. And again, it'll be nn.sequential it'll be a linear norm. In features is equal to indim. Out features is equal to outdim. Bias, they do it without bias. And then W init gain is relu. They use the relu activation function here. And so that means we do a nn.relu afterwards, and that gives us our activation. And that's basically it, right? Nothing crazy. There. Good. So we have our linear layers that we have here. We haven't done the dropout yet. There's one key idea that we need to talk about now. Def forward self x for layer in self dot layers for every single one of these prenet linear layers. We're going to do x is layer x, as simple as that. Now we need to do dropout. We're going to do f dot dropout, and we're going to do it p equals self dot dropout p. And here's the key idea. We're going to set training to true. And this does something explicitly. We're always doing dropout. So whether or not we're training our model or we're inferencing our model, we are always doing dropout, no matter what. So even during inference, we leave the dropout enabled. The reason we're doing this is that it allows for output variation. You can imagine that this prenet layer, we pass in an embedding, and it produces a projected embedding. And then this projected embedding goes through all of this machinery to then produce a new embedding. And we just repeat this over and over again. By having some random dropout on the output of this embedding, we'll get different types of outputs every single forward pass, right? So this allows us to have some output variation. This is kind of like adding noise or doing like a temperature parameter when you're decoding an LLM, right? You want some randomness in how the LLM generates, otherwise it'll always generate exactly the same thing, and that typically doesn't lead to the best results. So by adding some some of this variation, just some random removal of the prenet embeddings, then that can help produce some of this output variation. So that's why we're having training explicitly set to true always. Normally we'll do self.training here. Training. So this means when we throw model, when we do like model.train, then our self.training is true. When we do model.eval, self.training is false. But we're saying that we want this to always be true, no matter what, whether or not we're training or inferencing. Good, so that is our prenet, nothing crazy. Okay, so now it's time to actually implement our location layer. So we've covered, let's see here, going back again. So yes, we've covered everything through the prenet. So we have this right here. Now it's time to implement this location sensitive attention. The goal of this model, or this module, is to essentially look at how much emphasis has this specific decoding step of the Mel spectrogram, right? So remember, we're generating our Mel spectrogram one time step at a time, right? One step at a time. We want to look at how has this specific step attended to the different characters, right? To the different characters. And so this actually falls under a new kind of attention mechanism that we haven't really seen before. So let's maybe pull that up real quick. So additive attention. So it was proposed in this paper right here. Basically, the main idea is not only do we want, and it was proposed for a language translation, but instead of just learning a translation, what we want to learn is the alignment of the input to the output. In our case, it's kind of the same thing, right? We want our generated Mel spectrogram to learn its alignment to the different characters, right? Different characters. And so this actually works out kind of like, I think the formulation's right after the citations, right here. So this is the additive attention, and we'll see exactly how this all works out in just a bit. So don't worry about it just yet, we'll get there. But that's what this location sensitive attention is. So let's just start implementing it, and then it'll kind of make sense as we go. New class, location sensitive attention. nn.module, def init, self. And we're going to have an attention dimension. We're going to have a decoder hidden size. So as we are generating these kind of embeddings here, right, generating these embeddings in this LSTM layer, they're going to have some hidden size, right? So whatever that is, in our case, it's going to be, let's check. it's going to be 1024. So whatever it is, it's 1024. That's what it'll be. But attention will be computed at a different dimension. So we need to make sure we project our 1024 decoder embedding DIMs down to 128 to just do our attention at a compressed representation. So that's a decoder hidden size. We'll also similarly have our encoder hidden size, right? So I think that was 256. And then we have our attention and filters, like, okay, why are we doing convolutions and attention? You'll see in just a second. And then our attention kernel size, right? Attention kernel size. So let's get an idea here of what is going on. So let's do view. Let me add a show sidebar. Okay, yeah, good. Just add a couple extra pages. All right, so here's the thing. What we have right now is some character embeddings. And we've already pre-computed these, right? We know for our entire sequence of characters, we have some sequence of embeddings for them. And so that looks like this. We have sequence length, right? So this will, let's call them number of characters by our embedding dim, right? And we have these vectors for character 1, character 2, character 3, ... however many characters we have. But our decoder, the thing that generates the Mel Spectrograms, well, we're going to be generating one Mel time step at a time. And so again, this is where I'm going to be as clear as I can. I'm going to say time steps, so T steps. It refers to my Mel spectrogram. And then C steps, character steps, right? I'm going to try to keep the character steps is the basically which character are we on? So character, right? Let's try to make it as clear as possible. Because we have two different time dimensions, right? We have our time steps in our Mel direction, and then the character steps in the number of characters we have in our sequence, right? And so what we're going to do is this. Let's kind of think about it practically, and then we'll see how it's implemented. What we have is we've gone ahead and taken our embedding matrix here, had some E, but we used a linear layer, where we're going to use a linear layer like we saw right here, or we'll see in a bit. We'll use a linear layer to project this to some 128 in our case. So what we have is a character. So we'll have number of characters by 128 dimension here, right? So there we go. This will be our projection. And then what we have is a single, because we generate the decoder steps one time step at a time. So we're going to have the very first decoder step, right? Let's just do this one right here. I'm going to call this T0, right, for the first one. And this is also going to be some 128 embed dim. And when I do attention, what I learn is how is this specific T0 here related to the different character steps in our characters, right? So how is this one time step related to the different character steps? And once I compute that relation, I can actually produce a number, right? For this T0, I'm going to call this attention 0, right? Attention 0. It's going to be some numbers that represent how this one was related to these to all of these different time steps here in our characters. So let's say it's like at the beginning, right? At the beginning of the Mel, we would expect it to attend to the early parts of the sentence, right? Early parts of the characters. Because if we're saying something like the word hello, at the beginning, basically the acoustic embeddings we were producing should attend to H and E, right? The first couple letters, but the end of it should attend to L and O, like the ends of the end of my character, because it's monotonic, right? It's monotonic. As we go from left to right in my audio, right? In my produced audio, I should go from H to O in my characters because it's monotonic. And so what we're doing here is essentially that. So at the beginning at T0, we'd expect to place some emphasis at the beginning, right? 0.2, and then let's just say 0 everywhere else. So we only placed emphasis, and actually let's make it a little bit more realistic. We would expect to place 0. Let's say 3, 0.2, 0, 0, ... right? I'm just making up numbers. So there we go. We're placing emphasis here. And that's the first time step. Now, let's go back to our image. We're going to do this weird location sensitive thing. We'll see what that is. It's going to do some interaction here. Then we're going to produce a new Mel time step, right? A new one. We're going to, for the next time step. So now we're at T1. We're going to have T1. And this is going to be another embedding that's been projected to 128. for which we're going to produce a new attention, right? A1. And remember, this length here should be number of characters, right? Number of characters. How is this specific time step related to all the different characters here? So that's number of characters. So again, this is going to be another one. Now, if we go a little bit forward, we'd expect less emphasis to be placed in the beginning and maybe some more emphasis to be placed a little bit later. Right? And again, let's just say 0 for everything else. Again, this will be number of characters, just like that. And so these attentions is supposed to be, and what we're going to end up calling these, are our current attentions. The current attentions is how much emphasis does this specific time step place on the different characters. These are my current attentions. Very simple. And current attentions will be in the shape of batch, right? Number of samples I'm processing, by the sequence length. And in our case, sequence length will be number of characters, right? Very simple. But we need one more thing, right? This only tells us half the picture. This tells me how much emphasis is this character placing on these time steps. The other part of the picture is how much emphasis have I played on the different characters already, right? The different character steps. So this T1 is attending to these characters by this amount. But what I want to know is not only how much emphasis is this time step placing on these character steps, but also how much emphasis have I put on the different character steps in general? Like up till now, how much have I placed emphasis up till now? And so to do that, we can just do a cumulative sum, right? We can do C0 is just A0, right? C0 is just going to be A0. How much emphasis have I placed up to now? Well, it's just what I have now, so nothing crazy. And actually, let's make it more fair. C0 just starts as 0, right? C0 is just up till now, and then when we go to C1, it'll just be A0. This is how much emphasis I've placed up to now, and then C2 is going to be A0 plus A1. C3 is going to be A0 plus A1 plus A2. So it's just a cumulative sum of my attention weights, and it tells my model how much emphasis have I placed on all the characters in general up till now. And so there's two different things going on, right? We have the per time step attention weight, right? The current attention. How much attention am I placing on the different characters right now? And then the cumulative is supposed to be how much attention am I placed on the different characters up till now? And these two pictures give the model enough information to compute the alignment of how these time steps of my acoustic information are aligned to the character time steps. And this is processed through a convolution. A convolution. Why a convolution? Because a convolution is really good at looking at stuff like this. We have essentially a batch by 2, because we're going to have 2 features, right? One feature is going to be the current attention up till now, or the current attention, the attention right now, and then the cumulative attention up till now. So that's why it's 2 here. We'll have 2 features, and then we'll have the length. And then the convolution is just going to scan this and take a look at, well, I have lots of attention at the beginning, but not much at the end because I haven't gotten to the end yet, right? So this tells the model exactly, it basically can look at our attention weights and see where have we placed attention, where have we not placed attention. And it lets the model learn that alignment. So let's go ahead and start implementing that. This is pretty straightforward. So I'm going to copy, actually there's nothing to copy. So self.inproj is going to be the linear norm decoder hidden size to the attention dim. Bias is true. And W init gain is 10H because we'll be using a 10H attention or 10H activation function in a bit. And then self.enproj, encoder proj. So this will be the projection for our characters. Again, linear norm. It'll be the encoder hidden size to the attention dim that we want. They use bias as false here, so we're going to keep it that way. And then W init gain is 10H. There we go. And I missed the super location self.init. There we go. And so now let's write that convolution mechanism. So class location layer mn.module def init. And this is going to take attention, and filters. So the filter, number of channels in our thing, we have attention kernel size. and we have our attention dim. Because when we're looking at this, right, when we're looking at our sequences here, because our convolution is basically going to be scanning, like, you know, it's going to slide over this sequence here, looking at how much attention am I placing right now, how much attention have I cumulatively placed up till now. It's going to look at both of those features at the same time. Well, while it's doing that, we need to make sure we pick some reasonable context size, right? It needs to look at some length of this at a time, and I believe we select 32 for that, right? So we do 32 there. Or 31. Our kernel size is 31, and we pick 32 filters, right? 32 filters. So we're going to project our 2 channels, so batch by 2 by S to 32, and this is going to be done with a convolution of length 31. Simple as that. So let's go ahead, and this is implementation is very straightforward. We just need to do a quick super location layer self.init. And we're going to do self.conv is conv norm. In channels is 2. Out channels is attention and filters. There we go. Our kernel size is attention kernel size. And then padding, we want to make sure it's the same padding. We don't want to change the sequence length dimension or anything. And bias is false, right? Very simple. And then self.proj is going to be linear norm. We want to make sure we take this and then project it back to the attention dim that we want. Because we went from 2, we then project it to 32 right here, 32 filters, and then we're going to project 32 to the 128 embedding dim that we want for the attention layer. So we're going to do one more projection, attention and filters. It's going to go to the attention dim. Bias is false. W init gain is 10H, right? So def forward self attention weights, right? Our weights, which will, again, these weights will be in the shape of batch by 2 by sequence length. So then we can do attention weights is equal to self.conv attention weights dot transpose 1 2. Go ahead and make it sequence length by embedding dim, because that's how we typically process things. And then attention weights is going to be self.proj attention weights return attention weights. Simple as that. Okay, so this is our location layer. So this location layer is basically, again, it's a convolution that looks at our attention weights. What have we paid attention to? How have we related our current time steps of the Mels to the time steps, to the character steps of our characters, right? That's the relationship. And we want to learn the alignment between the two. So I'm going to call this self.what have I said, right? Like, what characters have I said already is basically what this is looking at, right? What characters have I already looked at? What have I already said? Attention and filters is going to be, yeah, so it's just that. We have our attention kernel size, and we have our attention dim. And we are good to go. So that's basically what have I said. Then we have self.energy proj is going to be linear norm. And here's the key idea. All of this stuff is 128 dim things, right? And we're going to do that formula, like I mentioned earlier, to compute the kind of the attention, the additive attention. But what I want is a single number that represents the overall like relationship. And so this is going to be a linear layer that takes our attention dim, which is 128, and projects it to just 1. Bias is false, and W init gain is 10H. We're going to project our 128 dimension down to 1, and we'll see why we do that in a bit. We're also going to add in one thing here. Our, let's see here. We're going to do def reset self, and this is for efficiency purposes. Self.enc proj cache is none. And so we can then throw a self.reset right here as well. The thing is that when we are computing our attention, right, these decoder steps right here, right, when we're decoding, generating one time step at a time, remember that our encoded stuff, this encoded text here is constant. It's the same for every single decoder step. It's always the same set of characters, right? These character embeddings. So we can just go ahead and cache it, right? Cache it, just store it as a variable, and then just keep it there, just so it's easy to access. So we don't have to keep passing it in over and over again. So we're just going to cache it right here, right? Just create a variable for that. Now, let's go ahead and do def calculate alignment energies. Self. This is going to take a Mel input, a encoder output. These will be all of our character embeddings. Cumulative attention weights, which we've computed up till now, and mask will be none, right? Because we're going to have an attention mask as well. So what we're doing is passing in a single Mel time step, right? As we decode, we pass in one Mel time step here, one time step that came out of the prenet layer. We pass in one time step. We have all of our character embeddings, and so let's go ahead and do our attention computation. So first, our Mel proj is going to be self.inproj to Mel input, right? We're going to go ahead and take our decoder hidden size of 1024, project it to the attention dim 128 that we want. But we're going to do this is currently a batch by, in this case, 1024, right? It's just a single vector that we took from, this will be batch by 128. It's a single vector that we took from 1024 and projected it down. But what we really want is batch by 1 by 128, so we can do broadcasting. So we'll see that in a second. So we're going to do dot unsqueeze 1, right? Just go ahead and add that extra dimension in. And then what we're going to do is if self.enc_proj cache is none, so this is the efficiency thing. I only need to do this encoder projection one time, right? I don't need to do it multiple times. So if it's none, then I can go and do it. When it's not none, then I won't do it, right? So it just saves us some compute from doing it over and over again. Enc_proj cache is equal to self.enc_proj encoder output, right? I'll go ahead and do that. And our cumulative attention weights, right? Cumulative attention weights is going to be equal to self.what have I set cumulative attention weights. So I call this cumulative attention weights, but this already has both things in it. It's going to be batch by 2 by sequence length. So this cumulative attention weight already has both the cumulative weights, sum up to this specific decoder time step of the Mel input, and also the current attention of this specific step, right? So we want to make sure we have both of them in there. So this already includes both of those things. And so we'll see how we actually produce this thing later when we write the decoder, right? That'll kind of come in there. But for now, that's the main idea. We have our setup, we projected our Mel, we computed our cumulative attention weights of what have I already said, how am I related. The convolution had a chance to look at my current attention weights and my cumulative attention weights to figure out which characters have I already attended to, which characters have I not attended to. And now that I have all of that, I can go ahead and wrap it up, right? We can do our energies is going to be self.energyproj. And actually, let's forget the energy proj for now. It's going to be torch.tanh, and it's going to be some of our Mel proj. So this is a batch by 1 by 128. How is basically just that one time step. And we're going to do plus self.enc_proj cache. This here is, again, batch by sequence length by 128. So I'm adding this one Mel proj here to all of the different time steps here. So I'm broadcasting this one time step, this one Mel step is added to all of my character steps. So I'm broadcasting them. And that tells my model how are these two things related together. So this is basically our additive attention, but then there's also what have I paid attention to already? What have I not paid attention to already? So that's me adding in my plus cumulative attention weights, because this again is going to be batch by let me check here. This is going to be batch. I think I did the transpose. So it's going to be batch by, again, sequence length by 128. So that's another feature. So what we're doing here is we're adding together. This is my current decoder step. This is all of my embeddings. And this is how much this specific decoder step has paid attention to these embeddings, concatenated with how we paid attention to these character embeddings up till now, right? The accumulation of them. And so this is my energies, right? Energies right here. And this will again produce basically a batch by sequence by 128. But what I want is one number representing for every single time step how much energy do I have, right? How much emphasis? What is my attention score, right? Basically that. How have I attended to these different things? And so we can do our energies is equal to self.proj, energy proj, and it's going to be energies. That's going to take this 128 and project it to 1. And so we can then throw actually a dot squeeze onto the end there, -1. And this will finally produce a batch by sequence, representing at this specific decoder step, we have paid attention to the different characters by this much. And it's basically just a vector for each one of them. That basically is producing these vectors right here, right? These vectors right here. How much emphasis am I placing? How much emphasis am I placing? And how much emphasis I'm placing at this step depends on how much emphasis I placed on the last step plus the accumulation up to that last step. And that's what you're seeing happen right here. A little bit tricky, right? But I'd recommend definitely going through it a little bit, but very important. This is probably the core part of this algorithm. So if mask is not none, because of course we have some mask, we're going to go ahead and do our energies is equal to energies.mask fill mask.bool, it's already bool, but just in case, negative float in, right? Go ahead and fill them with negative infinity because they have no energy. So energies. And this goes ahead and computes our local sensitive attention, right? Nothing crazy. So we can go ahead now and write our forward method, def forward self. And this is going to take in our Mel input, our encoder output, and our cumulative attention weights, and the mask, of course, mask by default, I'll just stick to none. And so our energies is going to be equal to self.calculate alignment energies, and this is going to be our Mel input, encoder output, our cumulative attention weights, and our mask, just like that. So that's everything we just did. And then our attention weights is going to be f.softmax energies dim equals 1. Because we want to compute, remember, we filled them with negative infinity, we want it to be a probability matrix. So we, just like we do in standard attention, we want this attention like vector here to sum up to 1 because it's easiest for it to be that way. It's more convenient for it to be that way. So go ahead and compute the softmax along them. And because these are negative infinity in the output, they'll just become 0, right? Just like we do in attention, right? Standard stuff. And so now finally our attention context, right? Attention context is going to be equal to torch.bmm, just matrix multiplication, attention weights dot unsqueeze 1 and encoder output, and then dot squeeze 1. So now that I have attention weights, right, of how is basically how much emphasis should I place on every single time step, then I should go ahead and do that weighted average. So if you can remember in our standard attention, we do softmax of QK transpose. I'll ignore the divide by you divide by a constant, but that's fine. And then you multiply it by V, because softmax QK transpose tells you the relationship between the different time steps. You do a softmax to make sure those relationships, the weights, add up to 1, and then you go ahead and just do that weighted sum of the values. Well, we're doing the same thing. We computed our attention weights. How is this Mel input related to the different outputs, the encoder outputs? Now that I've computed that relationship, I can go ahead and do that weighting. I can weight, basically my attention context will be a weighted sum of the characters. And that's basically it, right? Nothing crazy. And we just do this unsqueeze and squeeze just to make sure our dimensions line up, right? Because our attention weights, this will make it a batch by 1 by sequence. And then our encoder output is batch by sequence by embed dim, so we can go ahead and do all of those matrix multiplications together. And then we can squeeze that at the end because we no longer, it outputs a batch by 1 by sequence, right? Good, so that's our attention context. This is our weighted average of my encoder output. And so now I can return my attention context and my attention weights, right? These are my attention weights at this current step that I computed. And that's basically it, right? So that kind of sets up all of this machinery right here, this local sensitive attention. So let's just go ahead and start implementing the rest of this. Let's do the Postnet next. It's pretty easy. It's just a bunch of convolutions. I actually probably won't even implement this. I'll just copy paste it because there's nothing in it, just a couple of convolutions stacked together. So here we go. So we have a Postnet, and basically we have 5 different convolutions, and we just loop through, right? We're just going to do a bunch of these convolutions over and over again, and we're going to make sure that the input has some num mels. So remember, my final linear projection here, it's going to produce however many mels I have, in this case 80 mels. But if I just directly use these linear projections as my mel time steps, it'll probably work out pretty well. But the Postnet just adds a little bit more information. So we're just essentially going to take this 80 features. So we have basically an 80 by number of time steps, 80 by L. And so we can just do that. We have we have to transpose it because, you know, in our case, convolutions expect the 80 at the end and the sequence length first. So we transpose it, pass it through all the convolutions, transpose it. Each convolution is very simple. It's just num mels to however many filters we want in the Postnet. We go do a batch norm tanh dropout. Again, we do con norm, batch norm, tanh dropout over and over again. And then the final convolution again goes from the Postnet end filters back down to 80, right? So whatever it may be. And we do batch norm, dropout, standard stuff, nothing crazy. And this Postnet is just a residual, right? So we're going to go ahead and just add that to our input. And you can imagine it as a way of adding in missing information, right? As we generate something one time step at a time, there might be some information that's missing if you don't look at multiple time steps at a time that the LSTM may have missed. So the Postnet just does some post-processing of it, nothing crazy. So this is not really worth digging too much into. What is challenging is the decoder. So decoder, nn.module self. All right, then take a config, and this is where we start putting together everything that we have worked on up till now. All right, so we're gonna have self.config equal config, and I'm gonna copy a couple of these things in just because I don't want to type it. So let's start with the Prenet. So the Prenet, pretty straightforward, right? So our decoder has this Prenet, 2 layers. So we already wrote that earlier, so we can go ahead and paste that in. So we have a Prenet. Next, we have the 2 LSTM layers. Okay, no problem. How these LSTM layers actually work out is a little bit more complicated, so we're going to write it like this. Self.rnn is nn.module list. And what we're going to do is define 2 different LSTM layers, nn.lstm cell. This first cell is going to take config.decoder prenet dim plus config.encoder embed dim. And then we'll have the config, and it's going to project to config.decoder embed dim. There we go. So in this one, you'll kind of see how it all starts to work out. But this first LSTM cell is going to process the prenet output and my attention context vector, right? So I have 2 things going on here. I want this LSTM to look at the output of the prenet and also my attention context, right? So the attention context vector, the one that we produced right here, is the information of everything up till now, right? Basically, how much emphasis have I put on all the different character embeddings up till this specific decoder step? That's my attention context. And so the attention context, right? Attention context is how much emphasis have I placed up to this specific decoder step on all the different characters. And then the decoder prenet dim, the thing that this produces, is my new step. And so my first LSTM needs to process all the information up till now in that attention context of how I've placed in how I've attended to the different character embeddings, and then also my new time step. So I need to concat those together, and so that's why that's like this. And that's going to produce a single vector of size decoder embed dim, right? Decoder embed dim. The second one is going to be nn.lstm cell. It's going to be config.decoder embed dim plus config.encoder embed dim. Config.decoder. Okay, so the second one is going to look at my, again, the decoder and embed dim and the attention context again. So you're going to see how this comes together in just a second. So it'll make more sense when we actually implement it. We then have our attention. So I can go ahead and copy that in because we already wrote all the code for that. So there's the local sensitive attention. What did I call it? Oh, let's make it the same. So it should be local sensitive attention. There we go. So that's the attention mechanism that we just wrote. And then we have our next prediction. So we have these two different linear layers, one linear projection, or two linear projections, one for the stop token and one for the next Mel step. So let's go ahead and define that. We can do self.melproj. It's going to be linear norm config.decoder embed dim plus config.encoder embed dim to our config.num mels, right? So 80 in this case, so we're going to project to that. And then similarly, self.stopproj will be exactly the same thing. But this is just going to produce one number because we're going to do binary cross entropy loss for is this a stop token or is this not a stop, or a stop time step or not a stop time step. And then w init gain equals sigmoid, right? Because we'll be doing a sigmoid activation function here for binary cross entropy loss. And then we have our post-process net, right? The Postnet. So we can go ahead and copy you as well. Postnet. Okay. So this is probably the next challenging part, but after this we'll basically be done. So we're pretty close to the end. We need to initialize our decoder. Def init decoder self encoder outputs encoder mask is none. Right? Of course we'll have a mask, but that's fine. So our decoder will look like this. So we have b batch by sequence length by embed dim is our encoder output dot shape. That is what our encoder will look like, right? The embeddings of our encoder, the character embeddings. And we'll have our device is going to be equal to encoder outputs dot device. And so we need to initialize the memory and the cell state, right? So the hidden state and the cell state for our two LSTM cells. Because we're not using the LSTMs directly, like the standard LSTM in PyTorch. We're using LSTM cells, and we need to manually update everything ourselves, but that's no problem. We can just define it. So self.h, the hidden states, is going to be torch.zeros batch by self.config.decoder embed dim. Because remember, the size of the hidden states and cell states is the length of the output, basically the hidden size that you want. In this case, that's this right here, right? That size right there. It's going to be that. We're going to make sure it's on the right device. Device equals device for blank in range 2. Then self.c is going to be, again, torch.zeros batch by self.config.decoder embed dim again. Again, device equals device for blank in range 2, right? So there's 2 because we have 2 different LSTMs, right? So each LSTM has its own hidden state and its own cell state. So there we go. We then have our self.cumulative attention weight. This is going to be torch.zeros because at the beginning it's not like we have anything. Batch by s, device equals device. And then we have our self.attention weight. This will be our current attention weight, right? So not the sum up till now, just what are we right now? Again, torch.zeros, batch by sequence, device equals device. And lastly, we have our self.attention context. This is supposed to be a context factor that represents all of how is this specific time step related to all of the character time steps up till now, right? This is basically our attention context up till now. So we just need to initialize this as, again, torch.zeros batch by self.config.encoder embed dim device equals device. And the reason it's, again, of size encoder embed dim, because remember, that's exactly what we do right here. We did a matrix multiplication of our attention weights on the encoder output. So our attention weights could say, oh, put 2% emphasis on the first encoder output. The 5% emphasis on the second one, 10% on the third one, 20% on the third, fourth, whatever, right? So this is just a vector of probabilities that add up to 1, or percent proportions that add up to 1. Each of them are going to weight together all of these values right here, the different embeddings right here. And so that's it. So the output of this will just be the length, the dimensionality of the encoder output, because we're just doing a weighted sum of the encoder timestep, the characters, right? The character embeddings. And so we're good to go. That's our setup there. And then we have our self.encoder outputs is your encoder outputs. We can store that right here. And then self.encoder mask is our encoder mask, because this never changes, right? This is always, for every single batch that we pass into the model, this is the same. So we can just cache them and then reuse them and then replace them when we go on to the next batch. So nothing crazy. And then def BOS frame. We need a starting point for our decoding, right? And so you can pick anything you want here. You could have like a special beginning of sentence token if you wanted, but it's just easiest just to keep it 0. So it's going to be torch.zeros batch by 1 self.config.num mels, right? That's our starting point. Just a bunch of zeros because we have no information yet. And we can return start frame zeros. There we go. All right, time to start decoding. So def decode self and our mel step, right? So RNN input is equal to torch.cat. So like I mentioned, we want to concatenate together our current mel step, which right now is just zeros. There's no information there, but that's fine. And our current attention mel step and our current attention context, right? So this is my context information of how my time steps related to all the different character steps. And this is my current acoustic prediction, which right now is nothing because this is 0 and this is 0. So it's just a 0 vector, right? Because of course, at the beginning, there's nothing there. So that's my RNN input. And so first step is we need to pass our RNN input into the first LSTM cell, right? We have 2 LSTMs. Let's pass it into the first one, which is going to be this, right? Nothing crazy. Okay, so let's do self.h0, self.c0, because remember, we have 2 different hidden states and 2 different cell states. So the 0th one in each of these is for this first one right here. And then the first one here is for this, this one right here. So we're just going to update the 0th one right now because we're doing the 0th one. It's going to be equal to self.rnn 0. It's the very, the 0th one. We're going to pass in that RNN input. And we're going to do self.h0, self.c0, just like that. So that's me passing my data through, and I get my updated hidden and cell state from the previous hidden and cell state, which are just zeros right now, but have been updated to be something now, right? Whatever it may be. And then our attention hidden is going to equal to f.dropout. This is for helping with overfitting and all that. So h0, self.config.attention dropout p self.training, right? So this is gonna, this will toggle whether or not we're training and evaluating. This will, turn on and off. So this goes ahead, takes my hidden state, which has the dimension of, let's check again, dimension of my decoder embed dim, which again, up here, we set to 1024, and it produces that. So basically, my mel step is in the dimension of my postnet output, or my prenet output, right? My prenet output embedding dim. And then I also have my attention context, which is in the dimension of my character embedding dims. So what I'm about to pass into my attention mechanism is essentially just going to be the concatenation of the 2, right? So the first LSTM layer here is to process that. We have our current attention concatenated with our current time step of the Mel spectrogram, right? Which right now is just at the beginning, but that's fine. So there we go. We now have our attention hidden. Then our attention weight cat, right, is going to be equal to torch.cat, and we're going to concatenate together. We're going to concatenate together our cumulative and previous attention weight. So it's going to be self.attention weight dot unsqueeze 1. We're going to add that extra dimension so it becomes batch by 1 by sequence, right? So we've added that on. And then in the same way, we're going to do it for the other one as well. So self.q cumulative attention weight dot unsqueeze 1. And we're going to do it along the dim equals 1, right? Dim equals 1. So this concatenation will produce a batch by 2 by sequence. Okay? And now we can compute our attention context, attention weights is equal to self.attention. Self.attention. And we're going to pass in our attention hidden, our self.encoder outputs, our attention weights cat, and our mask is going to be self.encoder, encoder mask, right? Just like that. And what this does is for this, remember, this decoding is for one step of decoding. We will have to write a for loop a little bit later that's going to repeat this decoding for all the different steps that we want. So this is one step of decoding. And so now all we've done is we've produced my new attention context. How is this Mel step related to all of the different embedding steps, right? Or all the different character embeddings. And then I do a weighted sum of those character embeddings. And then I have my attention weights. How much emphasis has this Mel step placed on all the different character embeddings, right? All the different character embeddings. It's already been softmaxed and everything. So then my self.attention weight is going to be my new attention weights, right? This is how much emphasis I've played. And this is, again, because we've used that final energy projection, this is going to be a batch by sequence, right? Because it was batch by sequence by 1, and we removed the 1 by squeezing it, so it's just batch by sequence. And then we have self.cumulative attention weights. Well, this is just going to be self.cumulative attention weights plus attention weights, right? This is, as I decode, one step at a time, I want to add my current attention weights to the cumulative ones, so the cumulative one keeps track of all of the how much attention I've placed on all the different time steps up till now. And then this one is just for now, right? So this is for now, this is up till now. And that's the main idea. So that's my cumulative attention weights. And these two things, again, in the next decode step, will again be concatenated together and passed to attention. So you can see there's this loop forming, and we'll kind of do a trace through what's happening in a little bit. And self.attention context is just going to be the new attention context, right? This is my weighted sum of the characters, right? So there you go, nothing crazy. Now my decoder input is going to be torch.cat. I want to concatenate on to my attention hidden. My attention hidden being my current representation of my Mel step, right? Current representation of my Mel step, like as we see here. And we're going to concatenate onto it my self.attention context, right? My context, my history up till now. And then we can do dim equals -1. Go ahead and concatenate those two things together. And this is why the second RNN, as you see right here, takes that decoder embed dim plus my encoder embed dim, because my H0 here is of the shape or dimensionality of the decoder embed dim, and then so that's my attention hidden. And then my other one is going to be my attention context is at the dimension of my character embeddings, so whatever it is. So it'll be a 1024 and like a 250 or 256 or something like that. So that's my decoder input. And so now we do the other one, self.h1, self.c1 is equal to, again, f.dropout for helping with overfitting, self.h1. I totally missed a step. My bad. Self.h1, self.c1, my hidden in cell state for the second RNN. It's going to be self.RNN1. And we're just going to pass in our decoder input. And it'll be self.h1, self.c1. There we go. And then self.h1. And okay, so yeah, we're good there. And so then our decoder, there we go. Our decoder hidden is going to be f.dropout, self.h1, self.config.decoder dropout p, self.training. And then finally, we just have a couple things left to do. We need our projection. Our next pred input is going to be torch.cat. We want to concatenate on our decoder hidden, this is our prediction, to self dot, again, the attention context, dim equals -1. And so our next mel out is going to be self dot mel proj. Next, pred input. And then our stop output is going to be self dot stop proj. Stop proj. Next, pred input. And we can then return our mel out, stop out, and our attention weights, just so we can plot those in the future. Good. So we will, in a bit, go through all of this again, just so we're clear about how things are piping through, what's going on. So for now, let's just keep going real quick, and then we'll come back again. So let's write our forward method, because we're almost done here. Forward self encoder outputs encoder mask. We have our mels, and then we have our decoder mask. In this case, our mels is the entire sequence. It's all of our mels, right? And we'll see kind of how this works out in a bit. So when we start decoding, right, we need to start with a empty feature vector, right? So this was our start feature vector. It's going to be self.bos frame. We'll have our mels.shape 0.2 encoder outputs.device, right? So we go ahead, just start with that 0 vector like we had. That's why we wrote this method right here. We give it a batch size, just creates a 0 vector with 1 time step of the dimension of our mels, right? So 80. There we go. And our mels with start is going to be our torch.cat. We're just going to take our mels right here and just prepend the start feature vector to it, right? Just so it's easy. So we can do start feature vector, mels, and dim equals 1 along the time dimension. It's batch by time by embed dim. So we just go ahead and add an extra starting point right there. And then we can do self.init decoder, right? Because now that we're going to be starting our decoding, we can go ahead and initialize our decoder with the encoder output and the encoder mask, right? So we can go ahead and do that. This will, we can pass in our encoder outputs and our encoder mask. And so let's go ahead and create a list, or create a couple lists to just store some intermediate outputs. We're going to have mel outs, stop tokens, and attention weights. And it's going to be just 3 empty lists, because again, we're going to decode this 1 step at a time. So we're going to store them as we go. And then what we have is T decoding is mels.shape 1. Mels.shape 1, right? So how many time steps do we have? Well, we're going to go through whatever the longest one is, so max time steps. So there we go. And so now what we're going to do is for T in range T decoding, first step, if T is 0, so at the very beginning, we're going to do self.attention.reset. This is going to go ahead, and if we scroll back up here, it's going to go ahead and reset our encoder projection cache, right? Because we're starting with a new batch right now, so we need to recompute this projection of our encoded character embeddings right here. So we're going to do that here. So that just goes ahead and resets it. So when we do this next forward pass, it'll go ahead and compute it and then recache it, and then we're good to go. It won't do it again until the next batch, right? The next forward. Our step input is going to be equal to mel proj. We're going to grab for all the batches this specific time step and all 80 mel bins. So this is going to be mel proj. Oh, right, one thing I forgot. Let's go ahead and do that right here. We need to do mel proj is equal to self.prenet mels with start. So actually, now it's probably a good idea to talk about this. Our goal is to train basically an autoregressive model, right? We're going to predict the next mel time step given the previous one, or given the history of the previous ones, right? And so this is essentially just teacher forcing, the same way we train GPT, right? GPT, you generate one time step, the next token given the previous tokens, or the context of the previous tokens. And so because we're doing the same thing there, we're going to do the same thing here. We need to do that. But we need to make sure that we pass so every single time step, we're going to pass through our prenet here. And here's basically the main difference between how you train a typical autoregressive model and a teacher forcing model. In an actual autoregressive model, what we would do is pass in an input, generate something, right? And then use that to generate a new thing, and then use that to generate a new thing, ... We'd repeat that over and over again. Now that would be fine, but that would obviously accumulate errors as we go forward. The thing is that we don't need to do all that work. We know exactly what the correct answer is at every single time step. I know what the Mel bin is at the 0th time step, the first time step, second time step. So what we're going to do is just generate a step, but instead of passing in my generated step for the next one, right? Because imagine we're starting at time 0, we predict time step 1. Well, I know what time step 1 is. I have the correct answer. So let's just use that instead. So this is teacher forcing, where instead of actually doing autoregressive training, we're going to use the correct answers for my training purposes, but during inference time, of course, we have to generate autoregressively. So it'll accumulate errors, but that's fine. This is exactly how GPT works, right? GPT does exactly the same thing, where we essentially provide it exactly the sequence of tokens that we need, and we just want to do next token prediction, where here we're doing next Mel prediction. So we're always going to use the correct Mel to predict the next Mel. So if we're passing in t, we want to predict t plus 1 given the correct one. So that's one key idea. But because I know that each of these Mels need to go through this Prenet, right? Each of these things need to go to the Prenet. I could pass it through Prenet right here, one step at a time, but it's more efficient. Let's just pass everything through the Prenet right at the beginning, and then just use that, because it doesn't make a difference whether I do it all at once right here, or if I do it one at a time inside the loop, right? So I might as well just do it ahead of time and then just store it so I can use it. So that does my Mel project. I'm grabbing the tth output time step of my Prenet projected Mel spectrograms. Okay, good. So that's my step input. So now our Mel out, stop out, and attention waits. It's gonna be self.decode, the function we just wrote, decode, step, input. And then we can store Mel outs.append, Mel out, stop outs.append, stop out, or stop tokens.append. And then our attention waits.append, attention wait, right? So every time I do this step, I'm going to go ahead and store it, right? Store it in my list. And then at the end, we can just go ahead. I'll just copy this so I don't have to type it so many times. Right, we're going to take all of our Mel outputs, stack them together. Take all of our stop tokens, stack them together. Take all of our attention weights, stack them together. So I get my full kind of output matrices, right? Rather than a list of individual outputs. So this is me stacking on the time dimension. And then what we do is we take all of those outputs, and pass it through this postnet and then add it back in, right? Pass it to postnet. So we can take all of those outputs that we got from the Mel outs and post-process them with that postnet. Now, of course, not all of these time steps are valid. Some of these decoder steps, right, are not valid positions. So we have a decoder mask, we produce that. So I know which steps are real and which steps are not real. So I can go ahead and do a masked fill. Fill all of my Mel bins, so any predicted Mel time step that's outside of the real Mel time steps, just set them to 0. Same with our residuals, right? The output of the postnet, just set them to 0. Anything that has attention weights, go ahead and just fill those with 0, right? There is no attention weight on things that are not real time steps. And then similarly for stop tokens, just go ahead and fill it with a large value, right? In this case, 1,000. This way it'll, when we do the sigmoid, right, it'll just become 1. And if it's 1, that means it is a stop position. Because any position that's after my actual stopping point, well, everything is then should be stop tokens, right? Everything after. So we can just manually set that right here to make sure every stopping point is a stopping point, right? And so now we can return our Mel outs, Mel residual, stop tokens, and attention weights. And there we go. Inference mode, right? Let's write an inference script at torch.inference, right? Yeah, there you go. Def inference. Yeah. Self encoder output max decode step. So this is where you'll see how training and inference are slightly different from each other, but about the same. So what I'm setting here is that I will only decode up to 1,000 Mel steps. So there we go. And so I'll just kind of copy a bunch of the stuff that we already have. Right, so we have our start feature vector. Go ahead and initialize the decoder with these encoder outputs, our characters essentially. We have our encoder mask. In this case, it's none. The reason it's none is because I have only written this inference script to inference one sample at a time. So a batch size of 1, so in that case, there is no mask, right? We don't care about it. And then we have our intermediate, to store our outputs. We're going to start our input as this start feature vector, which is just nothing right now. And then we have attention.reset, right? Go ahead and reset that. And so our input is going to be self.prenet input. So here's one key difference from before. Remember, I mentioned that we just went ahead and just passed everything through the prenet right at the beginning because I knew what my mel steps were going to be, because I was going to use not my predicted mel step to pass into the next one, but rather the true mel step, because that's what teacher forcing does, right? We use the true input so our model learns to mimic the sequence rather than using our predicted ones, which would essentially accumulate errors, especially for training. It wouldn't work out so well at the beginning of training when the model doesn't know anything. So we're going to go ahead and just do that. But in this case, we're generating it one time step at a time. I don't have all of my mels here because I don't have any mels in general. I just have my single start feature vector. So let's just go ahead and project it with my prenet. After that, we can do our, let's see here. After our input, we can do our mel out is equal, mel out, stop out, attention wait is going to be self.decode this specific input, right? That'll go on to the next step. And then we can just store mel outs.append, mel out, our stop outs.append, stop out, and then attention wait .append, attention wait. And here's the trick. If torch.sigmoid stop out greater than 0.5, so with more than 50% probability, if we predict that, that means it's stopped, right? That means our model's saying we're done. So that's the important part of the stop token. It determines when we reach the end of our steps. L if len mel out. For some reason, if it doesn't predict it, then we can do, if it's greater than or equal to max decode steps, well, then we can do print reached max decoder steps, right? That means I set it to 1,000, so don't generate more than 1,000, and then break. And then finally, our input is equal to the mel out, right? And then we'll rinse and repeat, right? Just do this loop over and over again. Finally, our final output will be basically the same as before. We can go ahead and paste that in, right? So mel outs, we have this. Of course, we want to take all of these mel outputs that we had and post-process it with our Postnet, and then we return all of that information back, and that's basically it. And so let's just do a quick path here, just so we kind of put all of this in context and we understand where everything's coming from. But we can draw a really quick picture here. We basically have, and let me pull this up right here. We basically have a vector of mel, right? This is my mel step, one step of mel. And we have my current attention context of my weighted average, right? This is my attention context, a weighted average of all of my character embeddings for this specific mel step, right? Which at the beginning starts at 0, but that's fine. And then what we do is we actually have a sequence of them, right? A sequence of them. So I'll loop it back in a bit. So there we go. All of this goes to an LSTM, right? One step of an LSTM, and we produce a decoder embedding. And this is of size 1024, but that's fine, right? Some decoder embedding, some hidden state. And then this is then passed to a dropout layer, which is fine. So that's fine. This is what we have here. On the side, we have a couple other things. We have our attention weights, right? So we have our attention weights, and we have our cumulative attention weights that we've concatenated together, right? We concatenate these two things together. And we also have our encoder outputs, right? Which will look like this, right? Our characters. So this will be, again, num characters by encoder embed, right? Encoder embed dim. So we have all three pieces of information. And so our attention module, attention, looks at how is this specific time step of my input embedding related to all the characters and all of my weights, right, of how I've related, how much attention I've placed on things in the past. That's what this attention thing does. And this produces a new attention context vector, right? A new attention context. So they'll call this attention context new. This was the old one. This is the new one. How was this step here? This attention context, again, represents that. The relationship between my my input information right here, right? My input information right here, all of my character embeddings right here, and then how much emphasis I've placed on those different character embeddings, parameterized by this, right? My attention weights and my cumulative attention weights. So there we go. That produces this new value right here. Okay? And then what we do is we essentially store it. So we have a new attention weight. So this is going to produce a couple of things. A new attention weight. So we have our new attention weights, right? How much emphasis does this place on the different time steps? So we have a new one right here. So we're going to call this attention weights new. And I'm going to put red around them because they're brand new. So it's clear. So these two are new. There we go. And then what we do is essentially we update. Okay, so step one, we update this. So this is going to go and sum with my cumulative attention weight right here to update it, right? It's my new cumulative attention weight has to include the, the newly computed attention weights. So that means in the next step, when we actually pass it in, we're going to concatenate this information with this cumulative information, and we're good to go for that next step, right? So there we go. After that, what we do is we get our decoder. So our decoder now is going to be the concatenation of this attention hidden that we had right here. This one right here. This is going to be attention hidden, right? And we're going to concatenate these two things together now, right? These two things together now. And so that's going to go right here. Attention hidden, right? Attention hidden, and I'll call that right there. Yeah, so attention hidden. There we go. We go ahead and concatenate those two things together, the original one. Now that we've done that, we pass this through all of this, right? All of this through another LSTM layer, right? Another LSTM layer. And this is going to produce a decoder hidden, right? Decoder hidden. I'll call it DH, right? Decoder hidden. And then to this decoder hidden, I go ahead and concatenate my attention context, right? This attention context one more time onto here, the attention context. And this goes to my two linear layers to predict the next Mel and then the next linear. So it's a little bit weird, right? A little bit weird, but that's the main idea, right? The main idea is we want our LSTMs to understand, remember, the goal of an LSTM is to process a sequence, right? So this first LSTM right here, its goal is to process a sequence of Mels and the attention context, right? The projected Mels and my attention context. Because now that I've done all of this, we're on to the next step, right? This next Mel right here is going to go all the way up to become the new Mel right here. My attention context, which is right here, right, is going to become the new attention context right here. And we just rinse and repeat this whole process all over again. So it's a little bit strange to look at this, but this is essentially the setup, right? The first LSTM's goal is to process the Mel and attention context, the sequence of them, because the LSTM will keep track as we pass in one time step at a time. The hidden and cell state that we're storing keeps track of that historical information for us. It produces this attention hidden, which we then look at our embeddings. We look at our current attention weights and the cumulative attention weights, and we compute attention. This attention gives us our new attention context of how this time step was related to all of these character embeddings. It also produces new attention weights, which we use to update our cumulative attention weights up till now, right? And then this attention weight will also become this attention weight right here in the next step. We then go ahead and concatenate onto our attention right here, our attention context right here, our attention hidden, because attention hidden is my representation of my current step. Attention context is the representation of how this step is related to all the characters. So go ahead and concatenate this together. And now the second LSTM processes exactly that. How is my sequence of attention contexts of how this thing's related to the different characters, plus the information of those characters themselves related to each other, right? The sequence of those. That produces this decoder input, right? Then this decoder hidden, all we need to do is concatenate that attention context on one more time, go ahead and predict our next Mel in the next linear layer, and then these things become the input to the next sequence. So it's a very weird looking loop, but that's what we have, right? That's the main takeaway here. All right, so let's go ahead and wrap this up real quick. I can go ahead and actually copy this, right? There's nothing really going on here. We have our Tacotron, right? And Tacotron2 is basically just the encoder, the decoder. All we do is in our training, we go ahead and pass it in, right? Our encoder will take the text and the input lens, encode all of them. Then our decoder will look at all of that information, the encoder padded outputs, the encoder mask, the Mels, the decoder mask. And then finally, we produce the Mel outputs and the Mel residuals. So our Mel postnet out is just going to be the Mel outs plus the Mel residuals. And that's it, right? That's basically everything, right? So a little bit strange, but definitely more challenging than just transformer-based models, but I hope that made sense. So now we can go and quickly write a training script. Training is very, very simple. It's kind of exactly what you think. So let's go ahead and I'm going to copy a lot of this stuff because it's just standard boilerplate code. We just have all of our normal imports. We have our the stuff that we wrote, dataset, tokenizer, the model. We have all of our config stuff here, which just controls everything in the config that we've already looked at, plus some training stuff. And then we go ahead and initialize it with accelerator and all that. So none of this should seem new if you've already seen some of my implementations before. And also similarly, we can copy you right here, just loading our config file. So there we go. So that's going to go ahead and upload our Tacotron config, this Tacotron config that we kept referencing, right? So there we go. Okay. Training, relatively simple. We need a optimizer. It's going to be torch.optim.atom model.parameters. Learning rate is args.learning rate. Weight decay is going to be equal to args.weight decay, whatever we set it to. And then EPS is args.atom EPS, right? Our train set and test set, I'll just go ahead and copy all this too, actually. There's really nothing in here, just me calling all the methods we've written. We have our training data, which will just point to the training manifest, so the train split, the train CSV. Testing data, exactly the same thing, just points to the test split. And then we have our batch sampler that we wrote. We have and we're doing drop blast if we're training on multiple GPUs, just so it's easy. Otherwise you might get a error about all reduce, so it's fine. So we're just gonna go ahead and drop that last batch in the case that we have more than one GPU that we're training with. So we have a train loader, data loader, and then we have our prepare, right? And I'll just keep copy pasting as we go because I think it's just easier this way. There's nothing fancy in this. We're using a learning rate scheduler. It's just a simple exponential decay learning rate scheduler, right? So nothing fancy. We're just going to decay it from some starting learning rate to some minimum learning rate, and we want to do it over some number of steps. So here we go. We set this up like this, right? Nothing fancy. And then similarly, we can, if we need to train for multiple days, we want to be able to resume from checkpoint, right? So just go ahead and load that checkpoint in. And if we're using scheduler, then we have our learning rate scheduler here, right? So nothing fancy. Okay. So let's write our actual training loop. So for epoch in range completed epochs args.training epochs, right? So however many epochs you're going to train for, accelerator.print epoch, so we can print that out, and we can set our model to training mode, right? Model train. For text lens, Mels, stops, encoder mask, decoder mask, right? These are all the things that we produced with our data loader in train loader. We're going to put everything on the right device, so let's just paste this in, right? Just put everything on the correct GPU, wherever it is. And then we'll do Mel's out, Mel's postnet out, and stop preds. And then we don't need the attention weights right now because we don't really care about them. Is equal to model. We're going to pass in our text. Text lens.to. We just need to make sure, for some reason, it just needs, this has to be on the CPU for the padded padding, or the packed padding. So we're just going to make sure it's on the CPU because it's sanity checked, and then Mel's encoder mask and decoder mask. And there we go, right? Nothing fancy. Okay, so this is going to produce our Mel outputs and our Mel postnet outputs. And so now it's time to compute our losses. So what is the loss function for this? Well, it's actually quite simple. Our Mel loss is just going to be f.msc loss, Mel's out, Mel's. Right? So this is just the mean squared error loss between my true Mel's and my predicted Mel's. Right? Nothing crazy. Right? Just simple mean squared error loss. Our refined Mel loss is going to be f.msc loss. It's going to be between the Mel's postnet out and Mel's. And this is just a trick that they used. They made sure that when we compute the mean squared error between my Mel spectrogram, we do it for both the raw outputs of my LSTM, and we also do it to the postnet outputs of the LSTM. So we do it for both. We basically do it both. So this incentivizes both my raw outputs to get close to the Mel spectrogram, but also the postnet output to be close to the Mel spectrogram. And it's an incentivization thing, right? We want the model to be good already with the raw outputs, but then we want the refined outputs to just improve on it a little bit, right? So there we go. We have both of them here. And then we have our stop loss, and this is going to be f.binary cross entropy with logits, right? Because we never did a sigmoid in our thing. And then we'll do stop preds dot reshape -1 stops dot reshape -1 1. Just go ahead and just do the binary cross entropy loss between my predictions. These will be some, some logits. They'll be applied to a sigmoid. If it's greater than 0.5, then it's true. Less than 0.5, not true. And we want to make sure we can predict the correct stops from there, right? And then our loss is going to be Mel loss plus refined Mel loss plus stop loss, right? Nothing fancy. Then we do accelerator dot backward loss, accelerator dot clip grad norm, model dot parameters max norm is 1.0. That's just to help with stability. And then we have our optimizer dot step, and then we have our optimizer dot 0 grad. Right? Nothing fancy. After that, we can just go ahead and copy the rest of this because there's nothing going on. It's mostly just for plotting purposes, or to get our results. We have essentially our metrics, right? We have our losses. We're gonna, because if we're training on multiple GPUs, we'll grab them across multiple GPUs. We have our completed steps. Go ahead and print out Mel loss, the residual Mel loss, and the stop loss. And then go ahead and plot with weights and biases if we want to, right? Nothing fancy. Our evaluation is identical, so we can just go ahead and copy the rest of this. Actually, there's really nothing left in this training loop that's of scientific interest, so we don't need to break our head over it. There we go. So yeah, there's nothing going on. All we're doing is throw them all into evaluation mode, loop through our evaluation data, compute all the same things, go ahead and compute the average, and then this is just me making some plots of stuff as it's happening. So I'm not going to bother you with this, but all I wanted to do was plot my true Mels, my predicted Mels, and my alignments, right? Plot the alignments. And we'll see why that matters in a bit. I then go ahead and just average it up, store it, print it, log it in weights and biases. Simple as that. Okay, so let's see if this works real quick. Let me grab my run script here. So we're going to do new file run.sh, And there we go. That's the run script I used. You can try. I'm going to change the run name to Tacotron2 testing, whatever. That's fine. I need to create a worker. It's going to break, not be happy. Okay. I believe that's all correct. We have, in the worker, I need to create a new folder called save gen. This is just so it doesn't break on like a file path there. Okay, there we go. Batch size, learning rate. We have all of this. Let's get rid of weights and biases. We don't want to log with you. Okay, let's see what happens. I'm sure there's a bug in here somewhere. Okay, bash run.sh. Where's our first failure? Train taco.py. Oh, what did I call it? I called it, just train.py. Okay. Let's just rename you to train.py. Okay. Okay. Indices. Okay, let's go fix our batch sampler. So this should be for I in sampler. There we go. Okay, let's see right here. Train loader. We have trying to resize storage that is not resizable. Train loader. We have our, and actually let's make sure this runs on a single GPU just so it's easier to work with first. You can see it's actually a pretty small model, right? There's not really a lot of, it only has 20, about 30 million parameters, right? So a super tiny model. Let's see here. We have collate function. It's breaking on the collate function. Collate function map. Okay, let's see what's going on here. So in our, whoopsie daisy, we need to return the collate function, right? We actually, so basically it's a function in a function, and we're going to be returning this function to our thing. So that should hopefully fix that. Okay, encoder object has no attribute blocks, so now we're here. So we can look at our encoder self.convolutions. Let's see here. Self for blocks. So it should be in self.convolutions because that's what I called it. Is there a reason I changed the naming scheme? Let me double check here. So encoder. No, it should be convolutions. Yep. All right, let's keep going. All right, we're getting close. So refined Mel loss. So it looks like the forward pass worked. That's surprising. Let's check right here. Actually, it should be in the training loop. Refined Mel loss. What did I call you? Oh, I called it Mel's loss. My bad. Nice. All right, so stuff's happening. We obviously don't want to watch a training loop, especially because this actually takes some time. You can already see it starting to go down, which is kind of cool to see. Now, there is a couple interesting things that come when it comes to training these types of models, because what you'll notice is this. Let's stop you. Don't need to watch a training loop. Let's just look at the results, right? So if we look at workdir. Is this a good example? Yeah, it is. Okay. Yeah, this is a good example. So when we look at our results, right? So this is me. This is why I plotted the attention stuff with the true Mels and the predicted Mels as we're going. The thing is that predicting your Mel, like a time step of a Mel spectrogram is actually really easy, because remember, we are providing it. We're providing it the previous true step, not the autoaggressive, right? We're doing teacher forcing. We're providing a true Mel step, and we're asking it, given this Mel step, I want you to just predict the next one, right? Nothing crazy. So you can see right at the beginning of training, with like almost no effort, we predict everything almost perfectly, right? That looks pretty close. But notice our alignment here in that it actually hasn't learned any alignment, right? There is no alignment here. And so the model's able to predict the next Mel step easily because that's not a tough task. I just want to predict the next column here given the previous column, right? That's no big deal. The tougher part is learning the alignment between my Mel steps and my character indexes, right? So now this is the interesting part. So let's just kind of go through these one time step at a time. So that's 1, epoch 2. You can start to see it's learning this like, starting to learn something, right? Like we can see some information right here, but that's obviously not a good alignment. You can see some information like right here too. So 3, it's starting to get a little bit more, right? A little bit more. Let's skip ahead. 5, 6, 7, 8, 9, 10. And now you can start to see something happening. What we expect is kind of a diagonal, right? A diagonal. We want early decoder Mel steps, right? We want our neural network to learn early steps of our Mel spectrogram correspond to early indexes of characters, right? And if the sentence was hello, then our Mel spectrogram, the first parts should correspond to the H and the E, and the last parts should correspond to the O, right? Because it's monotonic. And so we have essentially that setup, right? We have that setup right here. And we can start to see some of that diagonality appear. Let's keep going. 11, and now you can see it really start to appear, right? So really it took about 10, 11 epochs for it to click in place. And now you can see it actually has, right? We see that happening. And then, of course, it's not perfect. Sometimes it disappears, but then it comes back, right? So we can see we get a strong diagonal dominance in our setup. And what you'll notice is if you inference a model that has poor alignment, you won't do anything because, again, predicting Mels is easy if you have the correct previous Mel. Predicting the next Mel with no information, like autoaggressively, is much more challenging. And then you're actually dependent on the alignment right here. And so getting this alignment is more important than getting these Mels here. And so the entire purpose of this fancy attention mechanism, like we did it, is it just comes down to the fact that we want our model to learn the alignment between our Mel bins, our time steps of the Mel, and the time steps of our characters. And that's it. That's the main takeaway that I want you to have. And so this is basically our alignment, right? Me computing again, each of these vectors are just a probability vector. So how much probability does this time step, like let's say time step 100, place on all the different characters? And you can see that it places most of its emphasis on these, whatever characters right here, and almost nothing anywhere else. And that's our alignment. Cool, right? So yeah, I'm not going to show much more than that. This was mostly just to show, let's see. Yeah, so I was just testing a bunch of stuff, but yeah, that's fine. So it seems to work out pretty well. But you can see, regardless, like the Mel spectrogram, we're always going to predict the Mel spectrograms pretty well. But it takes some effort to learn the actual alignment between the spectrograms and our characters. So after all of this, of course, all that's said and done, we want a model that can do TTS, right? Text to speech. So did we actually achieve that? So let's see here. I think I opened that notebook somewhere. Let me find it. I might have also closed it. Nope, not you. Not you. Not you. Okay, let me just reopen it again. So we have this right here. Good. So all I'm doing, very simple code. It's just an inference script that wraps our existing inference script. And all I do is I take my text, right? Some text I provided. In this case, I'm grabbing, so here's my function. I go ahead and just grab some text. I tokenize it, and I inference it with the inference script we already wrote in our thing. And the inference script produces both the output and the alignment. Right? And then I go ahead and print it out. Right? So I can play back my audio. Right? I can play back the audio, and I can see my alignment. And we can see we get really good alignment here. Let me see if OBS's audio is enabled. I think it is. So let's give this a try.
He had been in the employ of a corn chandler at Islington and went into London with his master's cart and horse.
He had been in the employ of a corn chandler at Islington and went into London with his master's cart and horse. right? So that's kind of cool. I can also provide my own sentences, right? So let's rerun it from the top. Workder, PyTorch. Oh, am I missing my? Let me. Workder. Where did I say this? Train taco. Oh, did I delete it by accident? Let me find it real quick. Let's just do this one here. Whatever. I think they all work anyway. So we have trained taco, trained Tacotron2, cat, attention, checkpoint 100. There we go. Oh, where's the oh, there we go. There we go.
He had been in the employ of a corn chandler at Islington and went into London with his master's cart and horse.
Right. So there we go. So that generates that. We can of course do it. So this is me grabbing a sample from my actual data set. I can also ask it to inference something specifically that I give it, right? So I asked it to predict, I can finally speak to you. There are so many things I would love to talk about. Do you have anything in mind?
I can finally speak to you. There are so many things I would love to talk about. Do you have anything in mind?
Right. So it can say what we say it. Now you'll notice two different things about this. One, there's poor prosody. Like the actual intonation in the way it says it is not all that good. So that's number one. And number two, it sounds very robotic. So the robotic problem will be solved with hi-fi GAN. So this kind of weird robotic nature to our generations is directly because of the inverse process, going from the Mel spectrograms, doing the pseudo inverse to get to spectrogram, and then doing Griffin lim to generate waveforms from our spectrogram. This is a typical artifacting of that iterative process, right? So it's good. It's good that it's generating what we're saying, but it's still not 100% there. That's fine. The other thing is prosody. So you'll notice that like the intonation of how it's saying things is kind of a little bit weird. And that's because this model isn't specifically tuned to do that. Modern TTS models have embeddings specifically to encode prosody, acoustic detail, things like that. And those are things we'll kind of explore in the future in more advanced implementations. But for the most part, this should give you a good idea of what's going on. I think it might be interesting actually to maybe listen to a example from hi-fi GAN. So maybe let's kind of give a little bit of a future of what we're getting to. So we're going to go to hi-fi GAN, and let's see if this works. So this is, oh, it's already open. Nice. Hopefully this just works without me having to, yeah, good. So I have here my true audio. That's fine. So this is me applying Griffin lim. This is me doing what we had just done, right?
He had been in the employ of a corn chandler at Islington and went into London with his master's cart and horse.
Not bad, right? Pretty good. But this is again the limitation of Griffin lim. Let's go ahead and try it with our Tacotron or with our hi-fi GAN.
He had been in the employ of a corn chandler at Islington and went into London with his master's cart and horse.
That's way better, right? That's significantly better. So this is me applying hi-fi GAN on this Mel spectrogram. So this is me taking a Mel spectrogram that I produced, and I apply Griffin lim to it, and I apply hi-fi GAN to it, and you can see that hi-fi GAN seems to work quite a bit better, right? It actually sounds like audio. And so we get this final like output here, and we can kind of compare some results to each other. Oh, I have to run U. There we go. So this will produce a bunch of outputs. So here's my output with Griffin lim.
I don't think I could love more than I already do.
Oh, more. Should we love you more?
I don't think I could love you more than I already do.
Okay.
I don't think I could love you more than I already do. I don't think I could love you more than I already do.
So it's close, right? Obviously, I mean, hi-fi GAN's not perfect, right? Because I again trained this on a super tiny data set, and hi-fi GAN takes forever to train. So to get it exactly right is a challenge. But this,
I don't think I could love you,
is way better than,
I don't think I could love you more than I already,
right? So this is what we'll be working on in the future. building a hi-fi GAN as well, because it's one of the most popular neural vocoders. There are some other methods that I want to explore, hopefully, like wave glow and some of these like normalizing flow-based vocoders. But we have plenty of time. We'll get to that in the future. I hope y'all enjoyed this, and I will see y'all in the next one.